Let's start recording first. So tomorrow, I can switch this camera. Okay, morning. Yes, announcements for today. Tomorrow, we have the exam. The exam format is a little bit different this time. I found a way that makes it easier to make multiple choice questions, but there will still be calculation questions. So be aware of that. You'll get more time per question this time around. I'm anticipating about 50 questions on the test and going to be giving you about 2 minutes per question. The other difference is that you're only going to be able to view one question at a time, and you cannot go back to previous questions. So work on the question that you're given. You've got more time now, but you can't be backtracking. You also have actually from tomorrow at noon until Saturday at 6 p.m. to take the test, to start the test, right? So you can start it. If you start it at 6 o'clock, I was wrong about this last time. I changed the deadline for people who seemed like they were going to try and take it at midnight for some reason. If you start the test with less than, so you'll get like 110 minutes or 100 minutes. So if you start the test less than 100 minutes before the deadline, the test will stop at the deadline, right? So if you start the test tomorrow at 5:45, you'll only get 15 minutes.
You mean on Saturday?
6 o'clock Saturday, right? So you have until noon tomorrow, Friday. Today is Thursday, right? So you have from noon tomorrow, Friday, the 4th, until Saturday, 6 p.m., June 5th. So you can take all day tomorrow to study or finish up assignments, work on other stuff, and then take the test on Saturday if you want, or you can take it on Friday if you want to have Saturday off. In terms of what's going to be on the test, right, this is cumulative, so there will be questions from chapters 1 through 4. There will be fewer questions from chapters 1 through 4, and the majority of the test will be on chapters 5 through 8. But that doesn't mean you can just ignore that first section. Are there any other questions before we get started on the chapter? Okay. So today we're kind of picking up where we left off, sort of where we left off yesterday. We talked about oxidation reduction reactions briefly. Today we're going to cover some more stuff about oxidation and reduction to round out your knowledge in that area. This is chapter 16, which does not mean we're skipping all the chapters in between. But chapter 16 in the book is where we cover oxidation reduction in depth, and this is just a portion of that. So, right, we talked yesterday about oxidation and reduction being this exchange of electrons in a chemical reaction. So, one definition of oxidation is the gaining of oxygen. So, oxidation, right? Oxygen. You can see how those are related. So, if we're adding oxygen to iron, we are oxidizing the iron. If we add oxygen to copper or oxygen in our here it says rapid oxidation, which is what fire is. We're adding oxygen to carbon in natural gas. Yes, Mel?
Where are these notes?
Oh, shoot.
There's no chapter 16 on Canvas, and the next one is chapter 8.
Nope, you're right. You're right. I know I mentioned this yesterday, but I didn't make a reminder for it. So let's take a brief moment here, and I'll upload those right now, and give you a little time to download these if you want to follow along. Yeah. I'm just going to put them in an announcement. See if I think uploaded them. I didn't even upload them. Okay. Please hold. So there's that. And then oh, I didn't make a handout version of those. Cool. Making the handout real quick, and then I'll post an announcement right now. So if you end up taking 1A and 1B, you'll talk about this more in depth. Talk more in depth about oxidation reduction reactions. I mean, you get more into depth on everything. And sorry about that. Course documents. Okay. Save that. Okay, so that announcement should have just gone out. And Canvas is slow. And then I'll also put a link into chapter 7. Because this goes along with chapter 7, right? We're talking about reactions. Work with me, Canvas. Okay. So we got those uploaded. Should be able to download them now. You can either go to the chapter 7 module or that announcement that I just sent out. Give you a few more minutes. I guess I'll have to edit this video today and chop this front end off. Okay. We good to go? Good. Okay. So, yeah. So one of our definitions of oxidation, right, is gaining oxygen. Oxidation, we add oxygen. Rapid oxidation. It's really the same process, just faster, right? Iron doesn't rust particularly fast. It takes a long time. You can speed it up with things like salt water. That's why cars along the coast will rust, or generally in worse condition. Also, cars in places where it snows, like the Midwest or the Northeast U.S., where they salt the roads, because that salt mixes with the melting snow, kicks up into the underbody of your car, and then things rust if they're not properly galvanized. So then reduction, when we talk in this sort of idea, when we're framing this in terms of adding or removing oxygens, oxidation is adding oxygens, and reduction is removing those oxygens. But redox reactions do not always involve oxygen. So like this lithium reaction right here, where we add oxygen to lithium to make lithium oxide, We could also have a reaction that is also a redox reaction when we're adding chlorine to lithium. So we can also define oxidation then as the loss of electrons, right? We talked about that yesterday, oil, and then reduction, oil rig. So oxidation is loss, reduction is gain. And we will see that here in a second again. Oh, somebody just joined the personal meeting room. Hopefully they find the Zoom links and open Discord. Okay. So, right. So oxidation and reduction must occur together, right? If there's an oxidation is lost. That electron has to go somewhere. It can't just disappear into the ether. It has to go somewhere. In the case of a chemical or like a battery, those electrons go then into that circuit. But in a reduction reaction then, so we always have to have something picking that up. So if we have one substance that loses electrons, then another must gain electrons. Keep Streamlabs up here, and then I make my webcam disappear there. So you just say, it just says gain there. So when hydrogen, in this reaction, when hydrogen is oxidized, that makes it the reducing agent. And this can be confusing. So hydrogen is oxidized, oxidation is lost. The reducing agent causes the reduction of another substance. So oxidation, so hydrogen, let me write this, right? So we're taking these electrons from hydrogen, and then they're going, well, they're actually going to the oxygen, right? So we're moving these electrons along to the oxygen. The oxygen then gains electrons. So the oxygen is being reduced. The hydrogen is causing the oxygen to be reduced. So the hydrogen is the reducing agent, and the oxygen is being reduced. And you can go the other way with this. So you could say then that the oxygen is reduced, so it's taking those electrons from somewhere. It's taking the electrons from the hydrogen, so that makes oxygen the oxidizing agent. So the oxidizing agent causes the oxidation of another substance. So remember, if something's being oxidized, then it is sort of it's the center of what is happening. It's oxidized. If it's oxidized, it's losing electrons. If it's the oxidizing agent, then it's making something else be oxidized. As you can think of it as like a spy, and it's stealing the electrons. Or if it's the reducing agent, then it's going and it's like a reverse thief. It's an agent of reducing. Just like the Joker was an agent of chaos. The Joker caused lots of chaos in Gotham City. Just like the hydrogen is reducing another substance. It's causing a reduction in another substance. I don't know if that helps. But I know how confusing this can be. Right, so we talked about this yesterday too. Oxidation is loss, reduction is gain of electrons, right? Oxidation is loss of electrons, reduction is gain of electrons. So we've got the oxidation. If something is oxidized, it's losing electrons. If something's reduced, it's gaining electrons. The oxidizing agent causes the substance is being reduced, and it's causing something else to be oxidized. If it's the reducing agent, the substance is being oxidized, and it's causing something else to be reduced. The oxidizing agent is an agent of change. So let's take a look at these, and we can identify which substance is being oxidized and which substance is being reduced. This is a little bit putting the cart before the horse, but we have here, and I'll just zoom in on this. So we've got potassium combining with chlorine to form potassium chloride. All right, we can look at this, see that the balance, the reaction is balanced, right? Our chemical equation is balanced. And we know that or I guess I'm telling you now, we will learn that if we have an element by itself, like we do potassium or chlorine, and remember chlorine is part of those Brinkelhoff diatomic elements, then the oxidation state, which we'll talk about here in a little bit, is 0 for both of these. So you have the free element by itself, the oxidation state is 0. And another way you can tell the oxidation state is sometimes based on its charge. It's not the same always, but it can be based on its charge. So if we look at potassium chloride here, you notice that their charge is 0, but we also know that this is an ionic compound. And potassium is in 1A, so it has a positive charge, right? A +1 charge. Chlorine has a -1 charge. So what we can deduce from that then is that we've taken an electron from potassium and given it to chlorine. Right? So if potassium loses 1 electron, its overall charge will be positive 1, because each electron has a -1 charge. And so then we gave one of those electrons to chlorine, so it now went from having 0 charge to having a -1 charge, because it has 1 extra electron now. So if we, oil rig, oxidation is loss. So potassium is oxidized, and chlorine is reduced, because reduction is gain of electrons. Okay, so I'll leave that sort of right there so you can still see it. And we'll move on to this next problem. So let's look at now, we've got charges now, so we can see these charges. And again, remember, if we have the element by itself, the oxidation state is 0. And if we have, in this case, and we'll talk about this more later, but here we have tin, right? Sn is tin, going from a 2+ to 0 oxidation state. And the only way in this reaction that we can change that, right, is by adding electrons. And then we see also that aluminum goes from a 0 to a 3. 0 charge or 0 oxidation state to a 3+ oxidation state. Also a 3+ charge in this case. So we can see that we're actually taking electrons, right? So if aluminum's 0, to get it to a 3+ charge, we have to remove 3 electrons. Those 3 electrons have to go somewhere, and so we're giving them to tin. This balances out because we've got 3 and 2, but so aluminum is giving electrons to tin, so aluminum is losing electrons, so aluminum is oxidized, and tin, because it's gaining those electrons to go from a positive charge to a 0 charge, tin is being reduced. And then we would also say that because aluminum is causing tin to be reduced, this would be the reducing agent, and tin is the oxidizing agent. So, all right, now let's look at this last question and think about this one yourself. Actually, this one's a little trickier, but think about this one yourself, and go ahead and drop in the chat which element you think is being oxidized and which one is being reduced. Don't worry about the oxidation. Don't worry about the agents for now. Let's try to identify which one's being oxidized and which one's being reduced. Anybody else want to throw something in the chat? Neither. Okay. So this is again where we need to talk about oxidation states. Because again, we have a 0 on both of these. But when these are combined, see, we'll talk about oxidation states. But for now, this, it's not an ionic compound. So I can see how you get neither. What's happening here, though, is we know that there's an oxidation reduction happening because one of our definitions of an oxidation is adding oxygen. So actually, carbon here is being oxidized. And what we'll learn coming up shortly is that when we have oxygen in a molecular compound or in a ionic compound, really, that oxygen, when it's part of a compound, has an oxidation state of 2-. So because we have an oxidation state of 2- here, and we have 2 oxygens, that's a total of a 4- charge, which means that our carbon has to match that in order for this overall charge to be 0. So carbon actually has a 4+. So the electrons then are moving from carbon to oxygen. Which one is the oxidation, or which one's being oxidized, and which one's being reduced? I know this stuff is very, very, very. It's hard to wrap your mind around. So today's lecture might be long because we're going to go very, very slowly because I want to make sure you guys are getting this. So here the carbon is oxidized because it's going from a 0 oxidation state to a 4. That requires that we are removing electrons from oxygen or from carbon and giving them to oxygen. So oxygen is reduced. Again, I think we have a lot of examples to go through. So, and if we get to the end and we're still feeling confused, well, then we'll move on and we'll hop into the homework questions, the even ones, if not the odd ones. Okay, so now we're doing the opposite, right? So we're identifying the oxidizing agent. Remember, so the oxidizing agent is causing something else to be oxidized, and the reducing agent is causing something else to be reduced. Okay, so we've got potassium and chlorine again, right? Same problem really as the one before. We can figure out the oxidation states of everything in these, of every element involved. Chlorine is going to be 1- here. Potassium is plus. We'll go over rules again for how to mark these oxidation states. But with these oxidation states in mind, now that I've written them out for you, which one is the oxidizing agent and which is the reducing agent? Right? So, yeah, potassium is oxidized and oxygen is reduced. Or sorry, chlorine is reduced. Yeah, so chlorine is the oxidizing agent.
Potassium is reducing agent.
Yeah. Yes.
But the potassium is being oxidized, right? That's the terminology.
Mm-hmm. Yeah, so one of the ways you can do this is if you just remember that agent means you're reversing, then you can figure out which one's being oxidized, which one's being reduced, and then you know that the oxidizing agent is going to be the one being reduced, right? So you can just kind of flip the names, add agent, and that tells you which one's which. It's confusing terminology. Okay, so on this one, we already have some oxidation states. But if that's 0 and 0, which one do we have being oxidized and which one do we have, or sorry, which one is the oxidizing agent and which one's the reducing agent?
Aluminum is reducing and tin is oxidizing.
Right. So aluminum is our oxidizing agent, or sorry, reducing agent. So I got to do this in my head too. Aluminum is being oxidized because it's losing electrons. So that makes it the reducing agent. And tin is our oxidizing agent. So again, we come down to carbon and oxygen. 0, 0. And then the oxidation state on the individual oxygen is -2, or 2 minus, and then 4 plus on carbon. So then, just using the rules that we did before, right, carbon is losing those oxygen, or those electrons. So that makes it the reducing agent, because it's reducing the oxygen. And then oxygen is our oxidizing. Because it's oxidizing the carbon. And oxygen, I can't think of an exception off the top of my head, but oxygen's almost always, if not always, going to be your oxidizing agent. It's part of the reason that it's, called oxidizing. All right. So when we talk about oxidation states, these oxidation states are the bookkeeping that we use to keep track of where electrons are going in these chemical reactions, right? Because we don't write out always where the electrons are. So all shared electrons are assigned to the most electronegative element. We haven't talked about electronegativity yet, but there's a periodic trend that's not too difficult. And you can think about it like this. Fluorine is the most electronegative. So if you move from left to right on the periodic table, you're getting more electronegative. And as you move from the bottom of the periodic table, from like 117 down here, up to fluorine, you get more electronegative. So what that ends up meaning then is when you look at carbon and sulfur, sulfur is going to be getting those shared electrons from their bond, because we haven't talked about covalent bonds yet. The oxidation state or oxidation number is computed for each element based on the number of electrons assigned to it. So oxidation state is not the same as ionic charge, which is important for a compound like carbon sulfide here, right? Because this is not an ionic compound. We've got two nonmetals bound together. So that's when the oxidation state can be the same number as ionic charge for ionic compounds. But in molecular compounds, there's not actually a 4 plus charge on carbon here. That's just how the electrons are shared. We'll take more of a look at that. So yeah, this is by far the easiest way to assign oxidation numbers, is you just follow these rules. Okay, so we've got the oxidation state of an atom and its free element is 0, right? We talked about that already. Copper, chlorine, right? So this is a Brinkelhoff. So if it's one of the Brinkelhoff elements, those diatomic elements, you know, Br2, O2, F2, that is their free element state. So these would all have oxidation states of 0. The oxidation state of a monoatomic ion is equal to its charge, right? So this is where I was talking about, if we have ions, then it is equal to their charge. But oxidation state and ionic charge are not necessarily the same thing. Then the sum of all the oxidation states of atoms in a neutral molecule or formula unit, right, if we're talking about ionic compounds, is 0. So the sum of all oxidation states is 0 in a neutral compound. In an ion, the oxidation state, the sum of the oxidation states is equal to the ion. Stop, Siri. Why? You don't. Sorry. I summoned Siri somehow. Okay. An ion is equal to, so for an ion, the sum of all the oxidation states is equal to the charge of the ion. Right, so we have this nitrogen's oxidation state, and we have oxygen's oxidation state, and in nitrate, those will sum to -1. For neutral molecules, it's 0. In compounds, so group 1 metals have an oxidation state of +1, and group 2 metals have an oxidation state of +2, right? So that on our periodic table, that's columns 1 and 2, or 1A and 2A from the periodic table. And in their compounds, we assign nonmetals oxidation states according to the hierarchical table shown at left, which we'll see on the next slide. And entries at the top of the table have priority over entries at the bottom of the table. So, right, so when we're talking about everything else, these group 1 metals have +1, group 2 metals have +2. The charges have to add up, or the oxidation states have to add up to the overall charge of the molecule or formula unit. The oxidation state of a monoatomic ion is equal to its charge. The oxidation state of an atom and its free element is 0, and free element for Brinkelhoff compounds is their diatomic state. So chlorine 2, bromine 2, oxygen 2, fluorine 2, so on. When we're looking at nonmetals, this is sort of the hierarchy of rules. So fluorine will override hydrogen, will override oxygen, will override group 7 and 6 and 5. So if we have, right, so magnesium fluoride, fluorine always has an oxidation state of -1. Hydrogen always has an oxidation state of +1. Oxygen, then -2, unless they're superseded by something higher on that list. So if we were to have something like F2O, I'm not sure that's even a real compound, but if we had F2O, then fluorine would supersede, well, I guess let's do this. So according to these rules, right, we say oxygen has a -2 oxidation state, fluorine has a -1 oxidation state, but our overall charge is 0. So we need the sum of these two oxidation states to equal 0. And to do that, we see that fluorine is the highest on this list. So oxygen will change its oxidation state to make this 0 charge, so that oxygen here has a +2 oxidation state. And then you can see that when we add 2 plus, there's 2 fluorines, right? So 2 times a -1, this equals 0. So a couple of lists here to, you know, in all reality, you should just copy these and have them on hand and just remember how to use them. So, right, so always follow the rule that's higher on the list. All right, so let's now, with these rules in mind, assign oxidation states to each atom in each substance. So for our first one here, we just have zinc. So remembering back to that table, if we have, I didn't make one for I didn't make a new slide for this, or a scene. Zinc is in its free element state here. So elements in their free element state have a charge oxidation state of 0. Monoatomic ions have the same oxidation state as their ionic charge. So we have a monatomic ion with copper here, and we see that it's got a 2+ charge. And since it's a monoatomic with a charge, then the oxidation state is +2. Now we're moving on to, we have calcium chloride. Okay, so now we're dealing with two elements. And we know, according to our rules here, let's go back and see, let's check this one first. Okay, so we're not dealing with any free elements. We're not dealing with an oxidation state of a monoatomic ion.
Okay, hold on. When you say monoatomic ion, you're meaning it's what? Okay, so what's the difference between copper and then calcium as far as whether it's a monoatomic or an atom?
Oh, it's monoatomic would be just a single atom. The difference between copper and calcium here is that calcium has a charge. So it could be copper, like you could have copper 3+. This would be a monoatomic ion.
And so, and then the oxidative state would be 3.
Yeah.
Okay.
Right. Yeah, so that is the only difference between those, is that one has a charge and the other does not. Because you could have calcium, and if it was just calcium like this, with a, no charge, that's now in its free element state.
0 oxidative state.
0 oxidative state, yeah.
Okay, I got it.
And actually here, I'll write this over here. Right, we're doing calcium chloride. CaCl2. So just looking at these lists, right, cancel it out. It's not 1, it's not 2. If we go to 3, the sum of the oxidation state of all atoms in a neutral molecule or formula unit, we have a neutral formula unit. It's got to be equal to, the oxidation states have to be equal to the charge on the formula unit, right? So the charge is 0. And we could also look at group 2 metals have an oxidation state of +2 in number 4. And calcium, even given as our example there, is an oxidation state of +2. But we still have to check over here. So I'm going to write CaCl2. We know that this is usually +2. And according to our hierarchy here, we have group 7A, right? Chlorine is in 7A. We don't have a fluorine, hydrogen, or oxygen, so there's nothing superseding that. And chlorine has a negative, each chlorine has a -1 charge. We have 2 of these. So we can go over here and we can say calcium's charge, right, is +2. And we're going to add 2 -1 charges. And this should equal 0. And if you do the math, it does. Right? So a couple ways you could have done it on this one really is you can find calcium and see that it's got a +2 charge and know that chlorine needs to have a -1 charge. And so the oxidation state for chlorine there is -1, calcium is +2. Look at carbon and carbon fluoride here, CF4, right? So we, again, swap over to this table, and we see, again, we're working with a neutral molecule. So we're going to be looking to make those oxidation states line up. And we can look at our table here. We have carbon and we have fluorine at the top. And we don't have a rule about carbon. So what we're going to do is, we're going to say, okay, fluorine has, so what is the, well, charge on carbon we don't know. But we know that in a neutral molecule, these have to equal 0. So, and then we know that fluorine has a -1 charge. Right? So don't know on carbon, we do know fluorine, and we know that it has to equal 0. So we can rearrange this then. Let's switch to the thicker pencil here. And we could say the charge on carbon, or oxidation state on carbon, excuse me, is equal to, right? So 4 times the -1 is going to be -4. Then we're going to add 4 to both sides. And we're going to see that the oxidation state on carbon is +4. So we're going to get then for carbon is going to, or for, yeah, carbon is +4, and for fluorine is going to be a -1. Nitrogen is a similar thing, right? So we got 2 nonmetals that we're dealing with here, and we have a charge on this ion. So we're going to look then to our table for our nonmetals. We have fluorine, hydrogen, sorry, what was it again? NO2. So we're working with NO2 minus. So we go fluorine, don't have hydrogen, we have oxygen. And oxygen is over group 5. So this oxygen will then supersede or override the rule for group 5. And again, so we need now our charges or oxidation states to equal -1, because that's the charge on our nitrate. And so then we know that we don't know nitrogen, but we know that we have 2 -2 charges for oxygen. Right? So then 2 times -2 is going to be -4. We're going to add 4 to both sides. So nitrogen will equal an oxidation state of +3. Yes, nitrogen will equal an oxidation state of +3. Oxygen is going to equal an oxidation state of -2. Right? So that when we add, we can just double check this. Right? We do 3 or +3 plus 2 times -2, because there are 2 oxygen atoms. This equals -1, which is the charge on our ion, so we know we've done it correctly. For our last one here, we're going to be, I guess I should be changing up my color here. So we could do, what we have, SO3, but SO3 without a charge. So again, look at our rules here, and we see that we have oxygen, and we have a group 6A, but oxygen supersedes the 6A, right? So sulfur would be a -2, but because oxygen is higher on the list, we're going to say that we know oxygen has a -2 charge. So go back over here, and we say we don't know sulfur, but we're going to be adding that to 3 -2 charges for oxygen. And we want that to equal 0. So 3 times -2 is -6. And we're going to add 6 to both sides. So the charge on sulfur has to be 6 or +6. Or, sorry, I keep saying charge. Oxidation state on sulfur is +6. And the oxidation state on oxygen is -2. Are there any questions there? When you're doing these problems, I would always start with your anion, or start with your less metallic, right? Because when we're naming these molecular compounds as well, like CF4, carbon fluoride, we put the most metallic one first. More metallic means more likely to form positive charges also. So if we have something like CF4, or if you had Cl or CCl4, CBr4, these compounds, you're going to want to look at this, because if we look at our hierarchy of rules for oxidation states, right? It's fluorine, hydrogen, oxygen. Oxygen or hydrogen is +1. But most of these are negative. And so you can start then by looking at the Br4 and the Cl4 and see what the oxidation state on your more positive or more metal-like element is going to be. So we'll do more examples, of course. I mean, this is kind of just another example of we're going to assign oxidation states, right? So we have carbon and sulfur, and again, right, we're starting with, in general, you want to start with the more electronegative element. So farther to the right and farther up to the top, closer to the top of the periodic table. We have sulfur. We don't have a rule about carbon, but we know that sulfur is in 6A, so it forms a 2- or 2- oxidation state. So sulfur, okay, yeah, right. So we have 0 on carbon, 0 on sulfur elemental, because these are in their elemental states. And then for carbon sulfide, then we have a 2- for sulfur. And we can use then, again, our equation. So we don't know what carbon is because we don't have a rule about carbon. But carbon plus, we have 2 sulfurs times that -2 oxidation state has to equal 0 because there's a 0 charge on this molecular compound. So we're going to get C. Carbon has an oxidation state. All right, so 2 times -2 is -4. So we're going to add 4 to both sides. And we're going to get +4 for carbon's oxidation state. So in general, oxidation is an increase in oxidation state. Right, so carbon is losing electrons. Carbon is being oxidized. Oxidation is loss. What we mean by that is if you think about it on a number line, when we say increase, that means moving to more positive numbers, right? +1, +2, +3, +4. Reduction is a decrease in oxidation state. Let me do that in this other color. Decrease in oxidation state. So that would be moving to the left. -1, -2, -3, -4. And we can see that here, right? So then sulfur is going from 0 to -2. We're decreasing its oxidation state. And so we're reducing sulfur. All right, so let's use oxidation states then to identify the element that is being oxidized and the element that is being reduced in this redox reaction. All right, so we want to just go through and we're going to assign oxidation states for everything. So easiest place to start, of course, is with those things that are in their elemental state. So tin, that is our only thing in an elemental state. A note here too, right? So we have nitric acid, HNO3. We're going to treat these as their individual ions. So hydrogen here is going to have +1, which also comes from our hierarchy. And then we know that oxygen is going to supersede nitrogen because it goes, let's see, in order of most important: fluorine, hydrogen, I think it was oxygen. Well, let's go back and double check. Right, fluorine, hydrogen, oxygen, and then 7, 6, 5. Fluorine, hydrogen, oxygen, and then anything in 7A, 6A, and 5A. Right, and fluorine's always going to be -1, hydrogen's +1, oxygen's -2. 7A from the periodic table is going to be -1, -2, -3. So that's sort of the hierarchy then. You can remember that sort of listing. So if we then look here to nitrogen, nitrogen is in 5A, so it's at the bottom of the list. And pretty much you're going to always be looking for fluorine, hydrogen, and oxygen to start with. So for this nitrate then, really not enough space on this slide. We have oxygen. We know oxygen is going to be -2 because it supersedes nitrogen. So we have -2 for oxygen as its oxidation state. We know that nitrate, NO3 minus, is going to be the charge on nitrate. So we're looking then to make nitrogen a positive charge, but it's going to be one less than the total negative charge on oxygen for all three oxygens. So we do 3 times 2 is -6. So nitrogen is going to be +5. Does that make sense? It's a little cramped up here, but we are plus for hydrogen, +5 for nitrogen, -2 for oxygen. So we'll move on to tin. We don't have a rule for tin, right? And we've got a neutral compound here. So again, if we check our list, right, it's going to say fluorine, hydrogen, oxygen. We have oxygen here. So that's a -2. And this is the same way too, right? If I asked you to write out tin oxide, I think tin is actually one of the, let me pull the periodic table here. Oh no, tin is not one with a single, okay. Anyways, so if I asked you to write tin oxide, this is the same way that you determine the charge on tin, right? So we would write tin, and then 2, and oxygen is -2. So that means tin has to be +4, right? So this would be tin 4 oxide. So we have +4 on tin, another -2 on oxygen. Keep moving on down the list. Now we have nitrous. This is one of those compounds that has a common name, or nitrogen dioxide. And again, right, so oxygen, we have our list, which is going to be fluorine, hydrogen, oxygen. Oxygen then is going to come above everything else. Nitrogen being a 5A at the very bottom of the list. So we're going to say, again, oxygen with a -2. You'll see a trend here. Oxygen, very often, -2. And because this is a neutral molecular compound, our nitrogen then has to have a charge that cancels out the 2 times 2 on oxygen. So it's going to be +4. And here, finally, we're getting away from oxygen being superior. It's met its match in hydrogen, so fluorine, hydrogen, oxygen. Hydrogen comes above oxygen. So we're going to use hydrogen then, with its +1 charge, to determine the charge on oxygen. Which for this means that oxygen still gets to be -2, right? So we have a positive oxidation state for hydrogen. 2, or 1 plus times 2 is 2 plus. And this is a neutral molecular compound. So oxygen is again -2. As a quick example for somewhere where hydrogen would supersede oxygen and change its oxidation state, if you have hydrogen peroxide, again, hydrogen, right? It's fluorine, hydrogen, oxygen. Hydrogen then has a +1. So +1 times 2 is +2. Oxygen in this case has a -1 oxidation state because it's -1 times 2 to be a -2. Okay, so we've written out now all of our oxidation states. What we want to look for is where oxidation states for individual elements change as you go from the left side of the periodic table to, or sorry, the left side of our chemical reaction to the right side, right? From our products to our reactants. Most of the time, again, because hydrogen, right? Fluorine, hydrogen, oxygen, because the priority or the ability of these elements to maintain their oxidation state is so high, we're almost never going to be looking for them to change their oxidation state. Most of the time it'll be something else. And the something else here being tin or nitrogen, right? Because then we move to the right side and we see that tin has 0 here, but tin has +4 here. +4 oxidation state. And then we see that nitrogen goes from a +5 oxidation state to a +4 oxidation state. Okay? So now, go ahead and in the chat, is tin, which one's being oxidized and which one's being reduced? Remember, oxidation is loss, reduction is gain of electrons. Yeah. Right. Yeah, correct. So tin, right, is going from a 0 to a 4. And if we remember, the other way that you can do this is if you think about a number line with 0 in the middle, as we increase our oxidation state, as we move positive, this is being oxidized. As our oxidation state becomes more negative, so I want to color code this. That's a highlighter. As we move more negative, we're being reduced. And you can see here too that this doesn't necessarily mean flipping from 0 to negative or 0 to positive or from positive to negative. Because when we look at nitrogen, for example, nitrogen is just going from a +5 down to a +4, but it's still moving to the left if you think about it as a number line. So it's being reduced. And then tin is going from 0 to +4, so it's moving to the right on our oxidation number line, and it's being oxidized. Yes, yeah, that's right, Brennan. If we think then about reducing agent and oxidizing agent, we just flip those, right? So nitrogen becomes our oxidizing agent, and tin is our reducing agent. Okay. Move on then. So just like regular, or maybe not regular, just like other chemical equations, chemical reactions, we need to balance this exchange of electrons. It's usually difficult to do simply by inspection, and so we use a special procedure called the half reaction method of balancing. So we take the overall equation and we break it down into 2 half reactions, one for oxidation and one for reduction. The half reactions are balanced individually, and then we add them back together. So this makes it easier once you figure out how it works. So let's consider this oxidation or redox reaction then, right? So we got aluminum plus silver is making aluminum 3+ and silver neutral. All right, so aluminum solid to aqueous aluminum and aqueous silver to solid silver. So we need to, first assign oxidation numbers to determine what's being oxidized and being reduced. This is pretty easy on this one because we've got monoatomic ions. So we can take a look, aluminum, right? So if we have anything in its elemental state, aluminum is 0, silver is 0, and then we have our monoatomic ions. So that's just +1 for silver, 3+ for aluminum. So then which one is being oxidized? We're oxidizing aluminum, right? That number is becoming more positive. And then we're reducing silver, since that number is becoming more negative. Okay, so then we write down the separate reactions for our oxidation and our reduction, right? So we're oxidizing aluminum. So we're going from aluminum solid. Actually, I need to give myself more space here. Aluminum solid to aluminum 3 plus aqueous. That's one of our half reactions. So you can see I just pulled out there everything to do with aluminum. And then we also pull out everything to do with silver. All right, so we go from silver plus.
Your pencil's a little bit a darker color.
Yeah, sorry, I can go to the thicker one. Here, I'll rewrite all this.
I mean, I can see you don't got it, but it's just a little bit, you know.
Okay. Well, I'll rewrite this then. Or I'll scribble everywhere. Right, so we're going aluminum is being oxidized. Silver being reduced. And then we're going from silver plus to silver neutral oxidation state as our reduction. Okay, so that's how we divide them into half reactions. It can get more confusing, but we'll work through examples, right? All right. So now that we have these half reactions, we can then balance them with respect to mass and charge by adding electrons. So we have the same number of aluminums on the left as we on the right, so we don't need to balance that any further, but we want the charge to be equal to 0 if we add up both sides. So we have, and let's do it like this. I'm going to put a plus here, right? Because on the right, we have a 3 plus, or a positive 3. On the left, then, we need to add electrons to cancel that out. So we'll add, each electron has a -1 charge. We add 3 electrons to the left side, so that our overall charge is 0 for that half reaction. Wait. Number of electrons lost in oxidation. No, I did this backwards. This is going to be aluminum plus 3 electrons, right? Because we removed 3 electrons from aluminum. So we still get the overall charge for this equaling 0. And so that's why here there's a space. So we have silver plus 1 electron. Actually, let's just leave a space here. 1 electron is going to be silver. But the number of electrons lost in the oxidation half of the reaction must be equal to the number gained in the reduction half. So do we do that on the next slide? I think we're supposed to do that here. So, right, so we lose 3 electrons with aluminum. Aluminum loses 3 electrons, so silver needs to gain 3 electrons. And we do that by adding a coefficient to everything in this half reaction. Right, so it's going to take 3 silvers, each losing 1 electron, to give us the 3 electrons that will be gained by aluminum. Or the other way around, I think. 3 electrons are lost there, so we need to gain 3 electrons from silver.
Can you go back? I was trying to write that.
Oh, sorry.
So, reduction part.
Let me know when you're good.
Okay.
Okay. So then we take our two half reactions and we add them together, canceling electrons and other species as needed. Okay, so we have 3, right? This is our 3 silver plus 3 electrons. Gives us our neutral silver. And we have aluminum becoming 3, aluminum 3 plus its 3 electrons. So we can cancel these electrons on either side. And then we get 3 Ag plus aqueous plus aluminum solid gives us 3 Ag solid. Doesn't really matter the order that you write these in, just as long as they're written correctly. Al3 plus aqueous. So then we verify that the equation is balanced with respect to both mass and charge, right? So we can count the charges on the left side. This is where I was getting ahead of myself. Count the charges on the left side. We have 3 Ag plus, so it's a plus 3 on this side. And we need that to equal the, right, 3 plus from aluminum on this side. So the total charge on either side has to be equal. So the procedure for balancing these redox reactions using the half reaction method, if we were to just write out a procedure, is we assign the oxidation states, we separate the overall reaction into 2 half reactions, which can be the trickiest part, then we balance each half reaction with respect to mass. So first you balance all elements other than hydrogen and oxygen. Then you balance oxygen by adding water, H2O. Then you balance your hydrogens by adding H+. And for basic solutions, which I think is more of a caveat for Chem 1A, but if you have a basic solution, then you want to neutralize all of your H pluses by adding OH minuses. So we'll add, and then you add the same number of hydroxides to each side of the equation. After that, then you balance each half reaction with respect to charge by adding your electrons. You make the number of electrons in both half reactions equal by multiplying, right? So that was where we added the coefficient to everything. Then you add your 2 half reactions together and verify that the reaction is balanced. It's a fairly lengthy process, but if you follow it correctly, it will get you the correct answer. So let's then take a look at this example. We have H plus chromium. So hydrogen plus chromium is equal to hydrogen gas, elemental hydrogen, plus this chromium ion. So first we want to go through and assign oxidation states. So we have +1 for hydrogen, 0 for elemental chromium, 0 for elemental hydrogen, and then +3 for the chromium ion. And now we want to break it down into our half reactions. So I'm trying to think of what you could type easily in the chat to break this into half reactions. But really what we're doing is we're isolating, right, hydrogen. This is an easier one. Hydrogen and hydrogen, and then chromium and chromium. So what we'll end up with is, and you should too actually label these, right? So hydrogen is gaining electrons, so it's being reduced. Chromium is losing electrons, so it's being oxidized. You can also tell because chromium is going from 0 to 3+, which is an increase or moving right on our oxidation number line, so that's oxidizing. Hydrogen is going from +1 to 0, which is moving left on the oxidation number line. So our half reactions then will be H plus goes to H2, Let's just say aqueous, H2 gas. And then our other half reaction will be chromium solid goes to chromium 3 plus aqueous. Okay, so now we've done, we've split up into our two half reactions. Our next step is to balance according to mass. So chromium looks good, right? We have one chromium atom on the left, one chromium atom on the right. But for hydrogen, we only have one hydrogen atom on the left, but we have two on the right. So we'll balance this by adding a 2 coefficient, right, to our hydrogen. Now that our hydrogens are all balanced, and I know that the, right, if we go back here, it says balance all elements other than hydrogen and oxygen first. But when you only have hydrogen, you can skip all the way to that. So our next step is then going to be balance each half reaction with respect to charge by adding electrons. So the charge on the right side, we want to be equal to the charge on the left side. So we'll add 2 electrons to the left side here, because we have 2 positive charges from the hydrogen, so we need 2 negative charges from electrons to cancel that out. For chromium, right, we're neutral on the left, so we need to make the right neutral. So we add electrons. 3 electrons to get a -3 charge to cancel out the +3 on the chromium. And now we want to go back and make sure the number of electrons in both half reactions is equal by multiplying, right? So we're going to multiply the entire reaction by some coefficient. And again, you can think about this kind of like the crisscross rule, because we have 3 electrons, we have 2 electrons. If we want those to match, we multiply each one by the other. So we'll multiply 2 by 3, and we'll multiply 3 by 2, so that we end up with 6 electrons on each. So that'll look like this: 6E minus plus 6H plus.
Where'd you get the 3?
The 3 is because of this number here, because there's 3 electrons here.
Oh, okay, I see. You're flip-flopping the electrons that you added.
I'm flip-flopping the coefficients on the electrons, yeah. If you end up with something, maybe we'll probably get an example of this later, right? If you had, let's say if you have 1 electron, and then you had, I don't know, 5 electrons in your other reaction, right? You're essentially doing the crisscross. You're taking this coefficient and multiplying it by 1. So this times 1, because we have electrons over here, and then you're doing 1 times 5, because we have this over here. But multiplying by 1 doesn't do anything. So really, you just multiply so that the number of electrons are the same. And you're multiplying everything in the reaction. Right, so that's why I have these parentheses here. And that's why we end up with 3H2 gas on this side. And then here we're multiplying by 2, so we get 2 chromium solid and 2 chromium 3 plus aqueous plus 6 electrons. The crisscross method is just a math trick. And it works a lot. It works for a lot of different things. Okay, so now that we've got both of our half reactions, and we've balanced them according to charge, and we've got the same number of electrons in each, we've done all of these steps, we can now add these together. And I'm going to zoom. So you can do, it doesn't matter which one you put on top, which one you put on bottom, but we're going to add them. And we want to line up. We want to line up our reaction symbol in the middle. All right, so then this is going to be the reaction sign for the chromium. So do 2Cr, solid, 2Cr3 plus. And this just makes sure that you're putting everything on the correct side. Okay, I'm actually gonna do one of these. No, sometimes this can be finicky, and we're gonna shrink it just a little bit to give me more room to work with. Okay, so now we need to add these two together, right? So we're basically just whoop, sum them up. We're gonna go 6 electrons plus 6H plus, and again, the order that you do these in doesn't matter as long as you get everything on the correct side. Still ran out of space. Okay. Our final step then is to cancel out. Really, we're canceling out things that are on both sides. So for this one, it's just, whoops, didn't mean to erase that. Our electrons, 6 electrons here, or 6 electrons there. And so what we have in the middle here would be our completed redox reaction. Cool? Yes, we'll take the break right now. All right, so I'll leave this up just in case anybody's still writing. We will take a 5-minute break. Be back at, we'll make it 6 minutes, 11:25. And poof, I'm back. All right. Let us move along now, because we got to get through this, and we got to get through chapter 8. All right, so let's balance another redox reaction then. All right, so we got redox
I've
reaction.
got a quick question here. I mean, the most confusing part about this,
Uh-huh.
how did we get to chapter 16? I didn't see that coming. I'm just like lost. So I've been waiting for that to connect, but
Yeah. So the reason is, right, so we did talk about oxidation reactions in chapter 7. But for the course objectives for this class, part of that involves more than just what we cover in chapter 7. So we're pulling a piece out of chapter 16, not doing all of chapter 16. This is just part of it. And just these, like, how to balance and use the half reaction method, because there's another method for balancing them, and there's other stuff about redox reactions and more complicated redox reactions, but we're not doing that. But I do apologize for not having that in the course module for chapter 7. I should have had this stuff in there beforehand. Yeah. So that's why we're on chapter 16. We're making a brief visit, and then we're heading back to chapter 8.
I can't wait to get back to the land of chapter 8 where it's a lot more comfortable. This is like chapter 16 should be called root canal chapter.
Yeah. Stoichiometry. That's the cursed word in general chemistry. Anyways, we'll get there. More fun ahead. So first, though, let's look at this. And we just have 9 more slides to go here. So the redox reaction here, we're looking at this in an aqueous solution. Not super important for this class, but it is a redox reaction. So can you predict then what the half reactions are going to be? Can we get either? I mean, obviously you can talk. Like if you want to just hop into the voice. There's not many of us here. What are our half reactions going to be?
It would be the copper 2 plus, and then that's nitrous oxide, right? Is the O3, is that?
NO3 is nitrate with the ion, and then to nitrous, yeah.
So yeah, so nitrate and nitrous.
Yeah, exactly. So we'll just do copper. I'll move a little bit faster on this one. Copper to copper 2 plus, right? And we should really say that this is solid. This is aqueous. And then we'll have the nitrate going to nitrous, nitrogen dioxide. Okay, so now we've got these. Oops, no 2. Now we've got these written out. We'll balance them according to the masses that we have here. So, right, our nitrogens are balanced, but our oxygens are not. So we need to balance. Sorry, I'm skipping copper, right? Copper just has copper. We're going copper to copper, 1 to 1. Everybody's happy there. But when we're looking at the nitrate, we have 1 oxygen, or we have 3 oxygens on the left.
But don't we need to add 2 electrons to the copper?
We'll get there. So we need to balance the masses first. Yeah. So I'm gonna do we're gonna balance all of our masses on both first, and then we'll come back and we'll do the electrons. But you're right. Happy there for now, I should have said. So if we flip back, let's flip back real quick. Just take a look at these rules again. Right, so we're going to assign our oxidation states. Oh, I guess we didn't do that. It was simple enough because we have the ions. But we should assign our oxidation states. We're going to separate into 2 half reactions. And we're going to balance each half reaction with respect to mass, right? So we checked for everything other than hydrogen and oxygen first. Then we looked at nitrogen, right? We looked at nitrogen first, I should say. That was balanced. We don't have enough oxygens on one side, so we're going to balance the oxygens. And then we're going to balance those oxygens by adding water, which means then we'll have to balance hydrogens. So that's why you go in this order. All right, so let's do that now. All right, so we need to balance, or actually let's do our oxidation states, since I skipped that step. All right, so copper as an element has 0. Oxygen, Write this out again. Fluorine, hydrogen, oxygen, right? This is -1, +1, -2. So oxygen is going to be superseding nitrogen because nitrogen's all the way at the bottom of the list at 5A. So we have a -2 for oxygen. -2 times 6, or times 3, skipping ahead, is -6. And we do have a minus charge here. There's a highlighter, right? There's a minus charge here. So we want our overall charge to match that as a -1. Since we have -6, that means nitrogen is +5. Copper, easy enough. +2, right? Because it's a monoatomic ion. And then for nitrogen here, again, oxygen is going to supersede. So we have -2. -2 times 2. We have a neutral molecule. So our overall charge is going to be 0. So -2 times 2 is -4. So we're going to have +4 for nitrogen. All right. And I will say it doesn't matter. So for practice, you should name these, right? So if we're looking at copper, going to copper 2+, we're going from 0 to 2+. To start with our number timeline, right? If we've got our oxidation timeline, we're moving to the right on the oxidation timeline. So that means that copper is being oxidized. Oxidation is loss. And then if we look at nitrogen, going from on the left side of the periodic table, or I keep saying periodic table, left side of our reaction to the right side of the reaction, nitrogen is going from 5 to 4, which is moving left. It's moving left on our oxidation timeline, so that's being reduced. Okay, so now we've covered that, right? So let's just write this. Nitrogen reduced. Oxygen. Oxygen. Come on. Copper. Oxidized. All right, now we're balancing again. We're going to add waters to balance our oxygen first. So we're going to get H2O. Now that we've balanced oxygen by adding water, we can balance the hydrogens by adding H+. So we have 2 hydrogens on the right that we just added. So we're going to add 2 H+ on the left. And now we can add our electrons to balance this charge. So we'll go back over to copper, right? So we want to neutralize this 2+ on the right side. We can do that by adding 2 electrons. So now that guy's balanced in terms of electronic charge. We can look over here on our nitrate reaction. And we have 2 H+. So we have +2 charge here. And we have a minus charge here, which gives us an overall positive charge on our left side, right? So +2 plus a -1 is equal to +1. So we want to balance this with the charge over here, which is 0. So we're going to add 1 electron. We're going to add our 1 electron. Let me put a little barrier in between these guys. So those are separate. Okay, so we added 1 electron. And if you want to look at it this way too, right? So we did it to balance those charges, but we know that because we did our oxidation states, we know that nitrogen is going from a +5 to a +4. And because we just pulled each of these into our half reaction, we're still a +5 on this nitrogen and a +4 on this nitrogen. So you can see that if we were to add this electron here to this nitrogen, we'd get +4 on this side. Okay, so we got our 1 electron. let's go back and check our list of rules. Right, so now we've balanced each half reaction with respect to charge by adding electrons. Now we make the number of electrons in both half reactions equal by multiplying. So we have 2 electrons in our copper, and we need to make this match with this reaction, right? We need to have the same number on each. So what we're going to do is we're going to multiply this guy by 2. And if you want to think about it in terms of the crisscross method, right, we'd be multiplying this side by 1. But because we're multiplying by 1, we don't really need to do that because it stays the same. So we can rewrite this one now as 2e minus plus 4h plus. And this is one of the places where you can get tripped up on these if you're not paying attention. You need to multiply everything by 2. Right, so then we have 2, NO3 minus going to 2 NO2 plus 2 H2O. Right, so it can be very easy to miss that when you're doing these. Now that we've got the same number of electrons in both, we can go ahead and add these together. So we have copper. Let me make sure I give myself enough room here. Copper going to copper 2 plus 2 electrons. Right, and then I'm going to work from the inside out here with 2 of these. Working from the inside out like this can just help you manage your space. Right, so that's the left side of our nitrate reaction. And let's use copper 2 plus 2e minus plus 2 NO2 plus 2 H2O. And now we go from the left, look at the left and the right, and we make sure that we cancel out all of the things that are the same on either side. So again, we have 2 electrons, which is exactly the same as the 2 electrons there. And so then our overall redox reaction is 4H plus 2 NO3 minus. Oh man, I forgot the copper, huh? Did somebody type that? Nope. Right, copper's in there too. My mistake. So our copper solid, and then we're going to have copper 2 plus 2 NO2 plus 2 H2O. So now we want to check and make sure that the charges are balanced on the left side and the right side. And so we'll zoom in again here, because these are the only charges that we have. So we look at our 4H plus, right? So this is a plus 4 charge. And then we have 2 times a 1 minus charge. So this would be plus a 2 minus. And that needs to be equal to, on the right side, we just have the 2 plus charge, right? So a plus 2. I'm going to write it this way, right? So if we do this math here, we're going to get plus 2. So we see that our charges are equal on both sides, and we've successfully balanced a redox reaction. Leave that there for a second. Okay. Let's just look ahead here and see if these are all examples. Okay, activity series, yeah, predicting spontaneous redox reactions. All right. Man, there might not be enough time today. Forgot how long these problems take. Okay, right? So our first step here, because we do need plenty of examples for these. Our first step here is going to be to write down our oxidation states. So we got to pick up the pace here a little bit. Again, oxygen, right? Fluorine, hydrogen, oxygen. Oxygen's a 2 minus, or -2 oxidation state. So we have -2 for oxygen, -2 times 4. Don't forget this ion. Right, so -2 times 4 is -8. We want a -1 charge, so we're going to have +7 for manganese. Tin, monoatomic, love those. Those are easy. Just a +2. And manganese also, right? So we have manganese +2 over here. These are monoatomic ions, so we just use their charge as their oxidation state. We're going to break this into our half reactions again. So we're going to get tin, solid. This is our easy one, right? So tin, 2+. If we want to right now, we'll just continue with this one and say, okay, so we got tin, going to tin 2+. Are our masses balanced? Yes. And we don't have any oxygens or hydrogens. So all we need to do is add our electrons. And now that guy's ready for the next step. And so now we'll move over, and our next half reaction is going to be manganese oxide.
I'm sorry, why is that +7? I don't get it.
Okay, so our we have 4 oxygens, right?
Yes, you got -8 oxygen.
Yep. So we got -8 from our oxygen, and we need to equal -1.
Because the MnO4 is negative already?
Yes, MnO4 has an overall charge of -1.
Okay, all right, got it.
Yeah, so if you've got a polyatomic ion, then you need to match the charge of the ion.
Okay.
Because that's where that charge is coming from. It's the mismatched oxidation states. Okay. So now we've got our second half here. We'll do manganese oxide. We've got tin, sorry, not tin, manganese 2+. So, right, so now we need to balance our masses, or our atoms, right? So we have 4 oxygens on the left. So to add oxygen, we add waters. So we add 4 H2O, right? And we're adding 4 because there's 1 oxygen in each of these or molecules. So that'll give us 4 oxygens. Now we need to balance for hydrogens. And when we balance for hydrogen, we add H+. So because we have 4 times 2, we have 8 hydrogens that we need to add. So we're going to do 8 H+. Now that we've balanced everything, right, we've got the same number of each atom on the left as we do on the right. Now we can take a look at balancing our charges. So we can do a little math to figure out what our charges need to be. So we have 8 hydrogens, so that's +8, right? Because 8 H pluses. And we're going to add a -1 for our manganese. And we want that to be equal to, we only have a 2+ on the right side. So 2+, so this is going to be a +7 charge equals 2+. The only way that we can balance charges at this point is by adding electrons.
And water's neutral?
Water is neutral, right? It doesn't have a charge listed, it's neutral. So then if we want to balance our charges here, we can only do so by adding electrons. So we need to get 7 all the way down to 2, right? So we're going to add 5 electrons. And since we're talking about charges here, right? So we're going to add 5 electrons, and that's 5 times a -1. So that's a -5 charge. So we're going to get +2 on the left and +2 on the right. So we'll add those just up here. We'll do plus. Again, try to give myself space, but I run them into each other. right? So we add those electrons. I'll move this. Come on. Right, so that was how we calculated the charges. So now we have both of our reactions balanced for charge, balanced for mass. Now we need to make the number of electrons match. And this is again where that crisscross method comes in handy. Right? So we have 2 electrons in our left reaction. Also this is also our oxidation reaction. Right? Because tin is going from 0 to 2 plus, moving right on the oxidation linear scale. Or wow, I just blanked on the word that I was using for that. Number line. Wow. And then we have on the right side, we looked at the charges for manganese, or the oxidation states for manganese. This is +7, and we're going to +2. So we're moving left on the oxidation number line. We're gaining electrons, so it's reduced. So this is our reduction. So if we look at our oxidation side, we have 2. And so what we're going to do basically is we're going to do this crisscross method, right? So 2 electrons means we're going to multiply over here by 2. 5 electrons means we're going to multiply over here by 5. And that's the quickest and easiest way to get matching numbers. Okay, so then we go through and we are going to do these multiplications. 5 tin goes to 5 tin 2 plus 10 electrons. Don't worry, I'll zoom out and leave it there for a little bit. And then we'll do 10. I'm going to put my divider here. 10 electrons plus 16 hydrogens plus 2 manganese oxide. And we're just multiplying everything here by this 2 manganese ions plus 8 waters. Okay? All right, so now we've done our oxidation states. We've identified our oxidation and our reduction. We split them up into half reactions. We then balanced our atoms, starting with oxygen first and then hydrogen. Then we added electrons to balance the charges on either side. And now we've made the number of electrons match between our oxidation reaction and our reduction half reaction. And now we're going to add the 2 reactions together. So we're going to get, right, there's going to be our 5 solid, going to our 5 tin 2 plus 10 electrons. Then we're going to have O4 minus, right, manganese oxide, 2 plus, H plus, and 16 of those, plus 10 electrons. For other side over here, we have 2 manganese ions, right, 2 plus ions, plus 8 H2O. And now we're going to get these 2 added together, MnO4 minus plus, let's do H plus 16 plus, I'm going to slip the tin in here, right, tin solid. And the reason I'm going to do that is because we're going to cancel the electrons anyway. Make sure you get every single piece of it. And then we got the right side. So we're going to cancel those electrons anyway, so we might as well write them on the ends. Tin 2 plus 2 manganese 2 plus 8 waters plus 10 electrons. Whoo, it's a doozy. Right? Okay, so we've got that done. Now we can go through and we can figure out what we can cancel. And because it's just the electrons, right, 10 electrons and 10 electrons, those match. You can think of this like a math equation too, right? If we were to move those 10 electrons from one side to the other, we'd subtract 10 from both sides. 10 electrons from both sides. And so they cancel out. And then the final step is to make sure that our charges match up. So we have, on the left side, we have our 16 hydrogens. So this is plus 16 plus 2 times the negative 1. That's going to equal 14, right? So we have a positive 14, and we should end up with a positive 14 on the right side. So we have 5 times positive 2 plus, move this over a little bit so I have space, plus 2 times another positive 2. So that's 14. And so we're good. These two match up.
Why don't we do anything with the 8 in front of the H2O?
Why don't we add that? You mean to the charges?
Yeah.
Because the water doesn't have a charge. Yeah, so we're just using, because we don't use tin on this side either, right? But that's because tin has a, well, it's a 0. It's just a 0 charge. So what we're doing at the end here is we're making sure that we balanced our charges. And so oxygen then would be the same in that it doesn't have a charge. Alrighty. Another redox reaction. Now, this is a redox equation occurring in a basic solution. And that is an important thing to note. We'll do this one. I'm not going to have basic reactions and basic solutions. No, not for this test. There won't be for this test a basic aqueous solution reaction. I will show you what that means when we get to that step. But first, let's look at our oxidation states, right? So we have fluorine, hydrogen, oxygen as our sort of hierarchy. Right, so fluorine's going to be -1, +1, -2. So this is important for our first element here, or first molecule, right? We have hydrogen. Hydrogen is going to supersede oxygen in terms of whose oxidation state is more important. So hydrogen has a +1. And then because we have 2 hydrogens, if you wanted to determine the oxidation state of oxygen, then we would say that this is, right, 2 hydrogens +1 charge plus, and it's a neutral molecule, right? So the whole thing has a charge, neutral charge. I always end up writing crooked like this. Can I? There we go. So because we have a neutral charge, right? So then what is oxygen? Well, it's going to be 2 times whatever oxygen's oxidation state is to equal 0. Okay, so then we have 2 plus, and I'm going to replace this oxygen with just X equals 0. So 2x equals 2, x equals 1. So our oxidation state, or sorry, that's a -2, -1. So our oxidation state on oxygen is -1. And again, I'll take this and Let me make a note on this one. Okay. Chlorine's a little easier. Again, oxygen is going to take priority. So it's -2. And then it's -2 times 2, which means that chlorine here, again, since there's 0 charge on this molecule, then chlorine needs to be +4. Right, so 2 times 2, -2 times 2 is equal to -4. And we're looking for an overall charge of 0. So chlorine is +4. On the right side, again, now again, right, so we have -2 for oxygen, but now we have a charge for this chlorate, or chlorite. So in this chlorite now, we have a -1 charge, and we know the charge of oxygen, or the oxidation state of oxygen, is -2. So we're going to do -2 times 2 is -4. Right, so we want a -1. This is equal to 2 times the -2. And then the chlorine here is going to be what we're solving for. So 2 times the -2 is a -4. We're going to add 4 to both sides. So we're going to get the oxidation state for chlorine is equal to 3. Then for our last element here, our last species in this reaction, we have oxygen as elemental oxygen, right? It's a Brinkelhoff. So its oxidation state is 0. And this is where it can get a little bit confusing. How do you now break up these into their half reactions? Every single piece of this has oxygen. The key for these is to look for the other elements that aren't in everything and look for where your oxidation states are changing. Right? So going from left to right, we can see chlorine changes its oxidation state from +4 to +3. You can also see that we have an oxygen here that's changing from -1 to 0. And that's how we can identify where our half reactions are going to be. So the half reaction for chlorine, or chlorate, or I guess hypochlorate, chlorite, gosh, so many names. We're going to have ClO2 aqueous. It's going to ClO2 minus. And our other half reaction then is going to be H2O2 reacting to form O2. Right? So identify where your oxidation states are changing, and those become your half reactions. Right? So we see oxygen, again, oxygen is going from -1, and it's becoming 0. So it's moving right on our oxidation number line. So it's being oxidized. And chlorine is moving from +4 to +3. So it's moving left on the oxidation number line. So it's being reduced. All right, so now we can go through and we can balance these. For this reaction involving chlorine, our chlorines are already balanced and our oxygens are already balanced. So we only need to add electrons. This one is a little bit different from ones we've done previously because now we have a -1 charge overall for the right side of our half reaction. And we want to make that balance
But doesn't
So
the side on the oxidized side there, don't we have to add a hydrogen to balance it?
for the oxidized half reaction,
Yeah.
I haven't gotten there yet.
Oh, I thought. Okay. Oh, okay. You're doing the coefficients for. Okay.
Yeah, I'm doing that reduction half reaction first. So we have right, so we have a negative charge here. We have no charges on the left side. So we have -1 on the right side of this. We need to have that same charge on the left side. And so that's where we will add our electron. So now we have -1 on both sides. Okay. Now I'll move on to the oxidized side. You're right. So now we do have the same number of oxygens. And if we were to go back to the procedure for doing one of these half reactions, for doing the half reaction method for redox reactions, we see that we want to balance oxygen first and then hydrogen. So we've checked, our oxygens are already balanced. So now we can balance with hydrogens. Because we have 2 on the left side, we'll have 2. Remember, you're balancing those with H+, by adding H+. So we now have +2 hydrogens on the right side. Now that we're balanced in terms of our numbers of atoms, we can balance our charges. So we have a 0 on this side. And this is important, right? Because we can only balance by adding electrons. So on the right side, we currently have a +2. So to cancel that out, we're going to add +2 electrons, right? So +2 times a -1. And that balances our charge. Because this would be 0 equals 0. Leave that for a second because I'm about to erase it. Okay. After this problem, we'll take a break too. All right, so now we're balanced. We have the correct number of electrons for the half reactions individually. Now we need to multiply to make the number of electrons equal between the two half reactions. So our half reaction on the right, we have 2 electrons. On our half reaction on the left, our reduced half reaction, we only have 1 electron. So we're going to take this guy and we're going to multiply by 2, right? And then if you're thinking about our crisscross method, we're multiplying by 1 over here. But multiplying by 1, it stays what it is. So we've got 2E minus plus 2ClO2 goes to 2ClO2 minus. I'm going to take the shortcut here. We're going to use this, right? So we multiplied here and we dropped it there. And then we're going to take these and add them together. So H2O2. And then we have O2 gas plus 2H plus 2 electrons. And then once we add these together, 2ClO2 plus our 2 electrons, which will ultimately disappear. And then we'll get 2 ClO2 minus plus O2 gas, 2H plus our 2 electrons. And again, I'm putting the electrons on the end, right? Because now this is the step where we look at either side of the reaction and we look for things that are exactly the same on either side so that we can cancel them out and simplify, right? So our 2 electrons and 2 electrons. And this then is our final balanced reaction. Oh, and right, one of the things we can do to check, the thing we can do to check is to check the charges on either side. So on our left side, ClO2 has 0 charge, H2O2 has 0 charge, so there's 0 charge on this side. On the right side, we have 2, and we have ClO minus. right? So that's a -1 charge. Plus, and we have also our hydrogens, and so we have 2 hydrogens, right? So that's why I'm putting a 2 here, and that's a +1. You can do this quick math in your head. 2 times -1 is -2. 2 times a +1 is +2. And this will be 0 as well. So we balance that. All right, let's take another short break before we finish it out. Let's do another 5 minutes. And we'll come back at 12:12. All right. I am return. Oh, I guess I'm a minute early. We can hold on for a second. Oh, it is very overwhelming. It's a lot. It is a lot. But you do have tomorrow. I'm always willing to go over more questions. You know, send me a message. I do spend most of the day on at this computer, even though my office hits 86 degrees, 88 degrees. All you got to do is ping me on Discord, or could send me a message directly. Or if I'm in one of the study rooms, if I'm in a study room, I'm in there because I'm waiting for people to show up and ask questions. So you can pop in there at any point.
How many of these are you gonna have on the test? I mean, it takes 36 minutes to do one of these. So if the test is 50 minutes long, that should be like, you know.
Yeah. Well, this is also the kind of thing that's hard. It's hard to put this into an online test, you know.
Okay,
so
good. So we can have 0. I'm totally fine with that. And
there'll definitely be like, calculate the oxidation states. There will be things like, in this reaction, what's being reduced, what's being oxidized, and I'm gonna do again, like I figured out some stuff with Canvas to do more multiple choice questions. Yeah, because I have to make multiple versions of every question to inhibit cheating as much as possible. Not saying that anybody is.
we would never cheat. What are you talking about?
Not saying anybody is, but it's one of those things you got to do, you know?
Yeah,
Okay.
so there will probably be like parts of it and the smaller sections, but there won't be like full questions like the ones we just did.
Right. Yeah, it'll be pieces, like it'll be individual steps. Like I might ask you a question, like give you a reaction like this and say, if you break this into half reactions, which elements would be in the half reaction, and then it'll be like a multiple choice thing, right? So when you're working with a multiple choice like that, you're gonna see stuff, and if you know how it works, it's not gonna take you 5 minutes to figure out. Shouldn't take you 5 minutes to figure out which one's going to be the half reaction if you're given 4 or 5 options. Easier to pick from those, but I don't think, if there is, I will take that into account on the exam, right? So 2 minutes per question, plus an extra 10 minutes or something, 15 minutes, if there is one of these that you have to work out in its entirety. Yeah.
Okay. I don't think any of us are going to complain if that's not the case.
Yeah, definitely not me.
Yeah. Right. All right. Goodness gracious. We still have to get through this. We might have to shuffle stuff around. We're going to get through this, and we're going to see how quickly Chapter 8 goes. There's not much more here. Chapter 8 is only 30 slides, but this was only 30 slides. It's just a lot of examples. Okay, so there's this thing called the activity series that we can use to predict spontaneous redox reactions. So if you add a magnesium strip into a copper 2+ solution, it's oxidized to magnesium 2+. But when you take a copper strip and place it into a magnesium 2+ solution, there's no reaction. So these redox reactions will happen spontaneous in one direction, but will not happen spontaneously in the opposite direction. So here, this is the reaction that, this is our reaction that works. If we flip this and instead do Mg2+ plus copper solid goes to magnesium solid plus copper 2+, this does not happen. Nothing happens. So there's this priority. There's essentially, and we'll see the essentially our tier list of metal cations and how much they want electrons and who they're willing to give electrons to, if you want to personify them and think about it that way. So the activity series of metals lists metals in order of decreasing tendency to lose electrons. So decreasing tendency to lose electrons. So at the bottom of our list, we're going to have the greediest metals. They are going to hold on to their electrons and they are not going to give them away to anyone. The top of our list has the metals that have the greatest tendency to lose their electrons. So you can think of those as very, very generous, right? They will give their electrons away to anyone. They are the most easily oxidized, right? Oxidation is lost, and therefore the most reactive. Right? And we talked about the ones at the bottom. They do not want to oxidize, don't want to give their electrons away. They want to hold on to those, and they will take electrons. If they don't have electrons, they'll take electrons from metals higher on the list. So we look at our half reactions. This is our activity series, right? So half reactions at the top are most likely to occur in the forward direction. So we have lithium, and lithium is giving up its electron. So lithium is the most likely to give up its electrons. And down at the bottom, it's the opposite, right? Gold, somewhat fittingly, is the greediest. It does not want to give up these electrons, and it will hold on to them. And if we have gold without electrons, it will take those electrons from anybody else. Okay, so if we have half reaction, any half reaction on the list is spontaneous when paired with the reverse of any half reaction below it on the list. We do got some examples. So gold is very low on the activity series, and because it is so difficult to oxidize, it resists tarnishing and corrosion. So that's why if you have pure gold, it doesn't tarnish, it doesn't oxidize. There's a special solution for dissolving gold called aqua regia. So it takes very, very specific conditions to oxidize gold. And yeah, metals used for jewelry such as silver and gold are near the bottom of the list. They're the least reactive metals, and that's why they're the most precious. So we'll use our activity series here real quick. And we'll check these out, right? So we have zinc. So let's go back real quick too. Look at this. So these are the reactions on this activity series and the direction that they're going. So when we look at our activity series, we're looking for the metals in their elemental state, right? These are all solid, 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 right? These are all solid in their elemental state. If you flip this table and reverse it, and then you're looking at gold gaining 3 electrons to form gold solid. Now gold Au3+, that's the most reactive, going in the opposite direction. All right, let's go back to this example, right? So we got zinc. So let's look at where zinc is. Or actually, yeah, let's leave this box here, right? We're looking at zinc because zinc in the forward direction, right? We have zinc 2+, so it's losing electrons. How likely is zinc to lose electrons? All right, so it's up here, somewhere in the middle. Now let's look at nickel. Right, so how likely, or where is nickel on this list compared to zinc? Nickel is below zinc. So zinc is more likely to give up its electrons than nickel. And thinking about this in the reverse, nickel is greedier than zinc. This nickel 2+, is going to take electrons from zinc more readily. So the quick and easy is you look at your metal on the left, or you look at your metal in your reaction, in your reactants. If it is higher than the metal that it's reacting with, then this is spontaneous. So let's take a look at this next one, right? So we have zinc again. We have zinc, oh, wrong one. Zinc again, right? Zinc, and then we need to find calcium on this table. Okay, we've got calcium. Calcium is higher on the activity series than zinc. Is this reaction spontaneous? Go ahead and you can either say it or drop it in the chat.
No.
Not spontaneous. 1 vote for non-spontaneous. Does anybody else want to add a vote? Does anybody think they're wrong? All right, no takers. You're right. That's correct. Because calcium is higher on the activity series, zinc is not going to give its electrons to calcium. And so this is not spontaneous. So what you want to look at when you have this activity series, you find which element is being oxidized. Because this is the tendency for oxidation, right? How likely they are to lose their electrons. All right, so most acids will dissolve metals by the reduction of hydrogen ions to hydrogen gas and the corresponding oxidation of the metal to its ion. So we're taking the electrons away from the metal, giving them to hydrogen to form hydrogen gas. So any metals above hydrogen on the activity series will dissolve in acids, while metals below hydrogen do not dissolve acids. This is the same concept. An important exception to this rule is nitric acid, which dissolves some of the metals below H2 in the activity series through a different reduction half reaction. Don't worry about that right now. Just worry about, we won't worry about nitric acid, but we have hydrobromic acid. So let's see, does silver dissolve in hydrobromic acid? So we have silver and we have hydrogen. This is the same question as is it spontaneous or not?
No, it does not dissolve.
Correct. It does not dissolve, right? Because we're in these dissolution, or if we're talking about dissolving a metal in acid, we're talking about taking it from its metal form, right? We're dissolving the metal solid in acid, and we're taking it, for silver, it would be a plus. So this is going from an oxidation state of 0 to an oxidation state of +1. So we're going, to the right on the oxidation timeline. This is being oxidized. So this predicts the trend for oxidation. You can predict this, use this to predict oxidation of a metal. So basically you check what your metal is. If something is below it and it's being oxidized, right? So if let's say we have potassium metal, potassium metal plus sodium ion to make potassium plus Na solid, right? Is this spontaneous? Yeah, right. It's below it. Now, I'm not going to do the opposite. I think it'll just be more confusing. So we're not going to go there because every oxidation involves a reduction. So you can always think about this in terms of oxidation. Okay. So that is the end of oxidation reduction. Now I need to somehow cover this, quantities in chemical reactions. And I think what I'll do is I will edit this video and we will go ahead and I will upload it as 2 separate lectures. But we got to get through this chapter today. Because otherwise it's on the next test, and that just means there's more on the next test. Or we do it tomorrow morning. There's not enough people to vote on if we want to do that.
Let's just bang it out.
Huh?
Let's just bang it out.
Let's just bang it out. We'll bang it out, and what I'll do is I will move the due dates for the chapter 8 stuff to Friday. Or not Friday, to Saturday. Or Sunday. When does that stuff due? Let's do this. We'll just knock this out. I'm going to go in and I'm going to do this before I forget. All right. Okay. So there's just a chapter 8 paper homework, which I think is due, tomorrow. So I'm going to change that due date to Saturday. All right. Saturday at midnight. You know what? Just make it Sunday. You should do the homework before the test because it's all practice for the test. But you have till Sunday now for that. Okay. So when we talk about chemical reactions, we're also looking at the relationship between these chemical quantities. And it's kind of like making pancakes. So we can predict the amount of products that form in a chemical reaction based on the amounts of reactants. And these are, the stoichiometry is the key to being able to predict these things. And this is really the core of chemistry. This is why we want to know, we do all this stuff with atoms and molecules, and we learn how to classify and group them together. We learn how they react so that we can predict the products when we do react them. So if we think about our stoichiometry, if we think about predicting the number of products that we're going to get with a number of reactants, you can use pancakes as an analogy. So our reactants are the ingredients for our pancakes. All right, so if we use 1 cup of flour, 2 eggs, and a half teaspoon of baking powder, we're going to get 5 pancakes. Right? We're not going to get more pancakes than that because we haven't added enough ingredients. So we start, 2 eggs, right? So if we have 2 eggs, now let's say that we have 2 eggs and we have extra flour, right? We've got a whole, 5-pound bag of flour, and we've got a whole full little can of baking powder, but we only have 2 eggs. How many pancakes can we make? Well, we could use extra flour, but we're going to get gross pancakes. We could use extra baking powder, but also, again, going to get gross pancakes. So the only number of good pancakes that we can make is the number of pancakes we can make with 2 eggs. So because we have more than enough of everything else, but we only have 2 eggs, we can only make 5 pancakes. And so we can write this as a relationship as a ratio, right? Assuming that there's enough of everything else, we get 5 pancakes for every 2 eggs. And you could use this too as a conversion factor. So we got 2 eggs for every 5 pancakes. Right? Let's say that we want to make 30 pancakes. How many eggs do we need? Right? And this is where unit analysis comes in. Wow, come on, Notability. Let me shrink it. It won't let me do it. If I move it first. Okay. This is where unit analysis comes super in handy, right? So we want to make 30 pancakes. We just multiply. How many eggs do we need? So we're going to, right, our pancakes here is going to cancel out. This will give us the number of eggs. So we just multiply 2 by 30, which would be 60. And then if we divide 60 by 5, we need 12 eggs. So this is the same concept that we're using and applying to chemistry. Because our, so what if we had 8 eggs, right? Assuming that we have enough of everything else, we're then using this as a conversion factor, right? Because we have 2 eggs, can make 5 pancakes. So we want to know how many pancakes we can make with 8 eggs. We do 5 pancakes for every 2 eggs, right? So I'm just taking the number from here, the number from here, and then we say, okay, we have 8 eggs, right? And we do it eggs on the bottom, eggs on the denominator, because then the eggs cancels, and you end up getting 8 times 5, which is 40, divided by 2, we can make 20 pancakes. So our chemical equations, our balanced chemical equations, are a recipe for how we combine our reactants to form new products. So the following equation shows how hydrogen and nitrogen combine to form ammonia. So we have our mole ratios, right? So we have 3 hydrogens plus 1 nitrogen gas. So 3 hydrogen gas plus 1 nitrogen gas gives us 2 ammonia molecules. So it's the same thing. We can draw up ratios for either the 3:2 or the 1:2. So if we wanted to say, if we want to do a ratio, how many hydrogens, right? Let's say, let me write this out. So one of these mole ratios could be NH3, you get 2 NH3s for every 3 hydrogens that you have. Or you get 2 NH3s for every nitrogen, right? For every 1 nitrogen that you have. And you can flip these because they're, again, very, very much just conversion factors. So we could even do NH3, right? For every 3 hydrogens, we get 2 NH3s. So we have these mole ratios that work out very similarly to, like we talked before, with our eggs and trying to calculate the number of pancakes we can make. And you can even, if you know the rest of these numbers, we can do, in this reaction, we're going to have in this reaction 3 hydrogens for every 1 nitrogen. So knowing this reaction, we can move and calculate the numbers of moles of each of these other elements or species in the reaction. Okay, so let's look at this example. We have 3 moles of nitrogen and more than enough hydrogen, right? Or as we might say, excess hydrogen. Hydrogen, just way too much hydrogen. How much ammonia can we make? So we're looking at the ratio then, right, between what we're given and what we're looking for. So we go to our reaction and we use these coefficients, right? There's an implied 1 here. We use these coefficients. We're not worried about hydrogen, right? Because we've got excess hydrogen. We only have 3 moles, so 3 moles nitrogen. And I think the traditional way to write out a stoichiometry problem is like this. And so we're going to have multiple cells in here, and within each of those cells, we're going to be multiplying, moving from one cell to the next. Okay, so our ratio, though, is 2 ammonias, and that's what we're looking for. We want 2 NH3s. We get 2 NH3s for every 1 nitrogen that we have. So we get 2 moles NH3 for every 1 mole of nitrogen that we have. And we can add mole in there as long as we're adding mole to the top and the bottom, right? Think about it. If we had, you can think about it like 1,000 again, to use that same analogy. 2,000, I'm just going to abbreviate thou, NH3 over 1 thou N2, right? That's the same ratio, but we're just counting more of them. And that's what we're doing here. So we have 3 moles of nitrogen times 2 moles of ammonia. Our units, again, cancel. So let me do that in red. Our units cancel here to give us units of moles of NH3. And so we'll find that we get 6 moles of ammonia when we have 3 moles of nitrogen. Hold on. I have to pause real quick. I will be right back. We're going to take just a brief break here. Just need to send an email. Okay. Sorry about that. I guess I'm going to come back and edit this anyway, but we're trying to find a house in Visalia. And the market is slammed. Okay, so where are we at here? All right, so let's do this now and look at how many moles. Let's look at how many moles of nitrogen are needed to completely react with 7.13 moles of hydrogen. Okay, so that's what I was talking about earlier. We don't have to just look at a reactant and the product. We can look at between two of our reactants. So let's say we want to completely use up our nitrogen, right? So we're combining nitrogen with hydrogen to form ammonia. And if we combine, and these combine at a 3-to-1 ratio, so then we will use up the entire, how many moles do we have to react with 7.13 moles of hydrogen to use up to completely react? Oh, I'm sorry. That was a mess. That was a word salad. All right. So you always want to start with what you're given. 7.13 moles of H2. Okay. I'm going to keep using this. So 7.31 moles of H2. And we know from our reaction equation up here that we have 3 hydrogens for every 1 nitrogen. So 3 moles H2 for every 1 mole of N2. So we're going to be looking for the amount, the number of moles of nitrogen to completely combine with this number of moles of hydrogen. So we're going to flip this and we're going to put 3 moles of H2 with every 1 mole of N2. And so then we just multiply, right? Because the units that we're looking for are moles of N2. We know that from the question stem. So then we want our units over here to be moles of N2, which is why we have here that we put moles of hydrogen on the bottom on our denominator so that it cancels with our moles of hydrogen in our given number. So we get 7.13 divided by 3 to get 2.34 moles. So it would take 2.3 moles of nitrogen to completely react with, or to completely combine with, 7.13 moles of hydrogen. Any questions there? All right. So looking at another example here, when water forms when hydrogen gas reacts explosively with oxygen gas, according to this balanced equation. How many moles of hydrogen of water result from the complete reaction of 24.6 moles of oxygen? Assume that there is more than enough hydrogen. Okay, so this is like, again, like our pancakes, except now we've got 24.6 moles of oxygen, and we've got excess hydrogen, right? So this is like when we had a limited number of eggs, and we had too much flour and too much baking soda or baking powder. So again, you want to start with what you're given, 24.6 moles of oxygen. And then looking at our question stem here, we can see that our resulting answer, we're going to want moles of H2O. So we were given moles of O2, and we want moles of H2O. So we look at our balanced reaction, our balanced equation, and then we can say there's 2 moles of hydrogen formed for every, right, an implied one here, for every 1 mole of oxygen gas that reacts. So our ratio is going to be 2 moles of H2O, excuse me, for 1 mole of O2. All right. I'll use the old format here just to show that they're interchangeable. So we got 2 moles then of H2O, right? Because this is what we're looking for. Should highlight this in yellow, right? These are the same units that we want in our answer. And we're using this ratio. So then our 1 mole of O2 will go here. 1 mole of oxygen. Our units then, right, cancel out. So that we get 24.6 times 2, 49.2 moles of water formed when we react 24.6 moles of oxygen. Right? And so we can take this sort of one step further on either end. Right? If we're given a mass of some species in our reaction, we can convert from mass to moles. We use our mole ratio from the balanced equation, and then we'll convert, that'll give us moles of what we're looking for, and we can convert that into mass, right, using our molar masses. So again, if we take now, right, this reaction, you can see that it's a hydrocarbon, right? Lots of carbon, lots of hydrogen being combined with oxygen. So we're burning octane here to form CO2 and water. what mass of carbon dioxide is emitted by an automobile when 5.0 times 10 to the second grams of pure octane is burned? All right. So again, we can identify just from our question stem what we're given and what we have. So let's use blue. We're going to highlight we're given this many grams of pure octane. And so this is octane. And we want to know the mass of carbon dioxide that is emitted. Okay, so let's do just real quick, just like on that previous slide, right? So we've got our solution diagram. We are starting with, here in the blue, grams being very important, of octane. And this is a great rule, right? This is a great rule. To compare and to do stoichiometry between two different molecules, or two different atoms, or two different species in a reaction, you have to convert to moles first. So we're always, if you're given grams, we're always going to convert to moles of, we're going to convert to moles of what we're given. We're going to change that from moles of what we're given to moles of what we're looking for. And then we can take our moles of what we're looking for and convert that into grams. All right, so we're going to do grams of octane. We're going to take that to moles of octane. We can convert from moles of octane to moles of carbon dioxide. And then for moles of carbon dioxide, we can get grams of carbon dioxide. So the first thing that we need to know is the molecular weight of octane. So, right, we've got C, we've got 8 carbons. I guess this is the way I would do it, is right, 12.01 times 8. And then hydrogens is 1.01 times 18. Punch it into the old calculator. Plus 1.01 times 8. Whoops. Yeah, I messed that up. 12.01 times 8 plus 1.01 times 18. And we'll get 114.26. Okay, so starting with grams of octane, 5.0 times 10 to the second grams of octane. We know the molecular weight. So the molecular weight, right, is in grams per mole. So if we want to get moles, we have to divide by the molecular weight. Because when we divide, that flips this to 1 mole of octane. 114.26 grams of octane. And see how our units there cancel? So then once we get the moles of octane, then we need to convert now moles of octane into moles of CO2. And that we just do from our reaction equation. So we have 16 moles of CO2 is produced for every 2 moles, of octane. Since we're looking for CO2, we're going to put that in the numerator. 16 moles of CO2 divided by 2 moles of, I'm just abbreviating it, octane is OCT. That's once we have our moles of octane, or moles of CO2, we can convert that into grams of CO2, right? So we have carbon, which is 12.01 times 1, oxygen, which is 16.00 times 2. So 16 times 2 plus 12.01, 44.01. This is again grams per mole. So we're converting from moles of CO2. We want grams. So since we want grams as our units, we're going to do 44.01 grams of CO2 on top. And 1 mole CO2 in the denominator, because when we multiply now, these units cancel. Moles cancels with moles, right? Because we're going to get moles divided by moles, and we're going to end up with grams. So once you set this up, you can just multiply straight across. 5.0 e to the second times 16 times 44.01 is that, divided by 114.26 divided by 2. And we're going to get black pen here, please. We only have 2 significant figures because that's what we started with. And everything along the way, when we do these mole conversions, these are exact, right? Because it's exactly that number of atoms combining with it, you know, they're exact numbers of atoms. There's no partial atoms. So then we can do, we'll get 1.5 times 10 to the third grams of CO2. I'll double check my math here. Yeah. Or 1 point, oh, sorry.
That's what I got also. I think it's right.
Oh, I messed it up. I messed it up when I checked it. All right. Yeah, 1.5. Yeah. Okay. So we always need to convert to moles first. And remember that molecular weight is in units of grams per mole. Sorry, I'll leave that for just a second longer. Okay. So again, we're looking at what mass of octane would be needed to generate 42.3 grams of water. Right? So we have very much the same problem with the same exact reaction, but now instead of looking at how much carbon dioxide we're making, we're given a mass of water. So we know how much water was produced. So this is like saying we made 20 pancakes. How many eggs did we use? Right? So it's just working this sort of a little bit backwards, but not really. But again, so we want to highlight what we're given, 42.3 grams of water, and then we want to highlight what we're looking for, mass of octane. Right? So we're going to say we have our grams H2O. We always go to moles first. Moles of H2O. From moles of H2O, we can use this ratio from our balanced reaction equation, and it has to be balanced. We're going to convert to moles of octane. And from moles of octane, finally, we can convert that using its molecular weight, 2 grams of octane. Right? It's the same thing. If we had, 20 pancakes, we know that for every pancake, there's going to be 2 eggs, or I don't remember what the ratio was exactly. I think it was 5. Was it 5 pancakes for two eggs? So for every 5 pancakes, we're going to use 2 eggs. It'd be like saying we have this many grams of pancakes. How many grams of egg did we use? So you'd have to figure out the mass of each pancake, right? And then you could use that mass per pancake to calculate how many pancakes you had. And then go back to eggs. So we're starting with water. So we got 42. And I'm going to do it this way this time. I can make this draw. Oh, no. Didn't do the straight line. Okay. I'm going to do it like this. So we have 42.3 grams H2O. Right? To convert from grams of water to moles of water, we need the molecular weight of water, which is 18 So it'd be 18.02. That's 18.02 grams of water for every 1 mole of water. And then we can look at our table or our balanced reaction equation, right? And we see we have 18 waters for every 2 octanes. So if we wanted to write that, right? So 18 H2Os for every 2 C8H18s or octanes. But what we want is octane. And what we have currently, right here at the step that we're at is moles of water. So we're going to do 18 moles of water for every 2 moles of octane. And now we use the molecular weight of octane, which we calculated before as 114.26. Right, 114.26 grams of octane for every 1 mole of octane. So when we go through and we check out our units to make sure that we did everything and we got all of our conversions here correct, we can see that we have grams canceling with grams, right? We have moles and moles, so those cancel. Moles of water and moles of water. We have moles of octane and moles of octane, right? So that whatever's in the top left should be matched in the bottom right to calculate or to cancel. And then our resulting units are grams of octane. $42.3. So then we just multiply straight across the top. 42.3 times 2 times 114.26 is equal to that, divided by 18, divided by 18, oh, I should have done 18.02, divided by 18. So we will get, again, we started with, 3 significant figures, so we'll end with, we're not ending with 3 significant figures because we started with 3 significant figures, we're ending with it because we're multiplying and dividing, and 3 significant figures is the fewest number that we have for all of our conversion factors, excluding these mole to mole conversion factors, which are exact. So we have 3, so we're going to get 29.8 grams of octane. Cool. All right, so we got magnesium hydroxide now, which is the active ingredient in milk of magnesia. And it neutralizes stomach acid, primarily HCl, according to this reaction. So how much HCl in grams can be neutralized by 5.50 grams of milk of magnesium hydroxide? So we are given, if you wanted to check real quick, we can look at this and see that we're given a balanced chemical reaction, which is good. And again, we want to look at what are we given? We're given grams of magnesium hydroxide, and we are looking for HCl in grams, right? And so the way you can get tripped up on these is these units, right? Because this doesn't have to be grams. This could be kilograms or milligrams. Always make sure that you're going to grams first because the mole conversion or the molar mass, right? Molar mass is in grams per mole. So we're going to do a reaction diagram here, or a solution diagram. We're starting with grams, MgOH2, right? From there, we always want to go to moles first. So we're going to go to moles, MgOH2. Once we get that, we can use our conversion factors here from the table because we want to know how much acid how much acid, HCl, we can neutralize. So these are the two species that we're interested in terms of their mole ratio. And so we're going to go from there to moles of HCl. And then finally to grams of HCl. Right? So again, we can just see if I can get it. Oh, there's the straight line. Okay. Ahaha. Not sure how long I have to wait to get that straight line. Okay. All right, so this is going to be our solution diagram, and then it's pretty easy to write out this sort of grid that we're going to fill our numbers into based on the solution diagram. So we're starting with 5.50 grams MgOH2. So our first step, right, we need to figure out the molecular weight of magnesium hydroxide. Okay, magnesium, oxygen, hydrogen. I have a periodic table here. This periodic table, which is hard to read, but I can read it off to you. So we're starting with magnesium is 24.31. Oxygen, right, we got 16.00, and these ones you should know, 1.1001. Now for the numbers, remember that we've got our hydroxide, our oxygen, and our hydrogen are within these parentheses, so there's 2 of each of those. Times 2 times 2. So we'll do 24.31 plus 16 times 2 plus 1.01 times 2. For molecular weight, 58.33 grams per mole of magnesium hydroxide, right? And again, we're converting to moles. So remember, the unit in here, our unit here is going to cancel with our units down here. And this up here will give us the units that we want. So we want moles. So every 1 mole of MgOH2, we have 58.33 grams MgOH2. Then we're converting, so we've calculated our moles of magnesium hydroxide, right? Started with grams, calculated moles. Now we need to calculate our moles of HCl. And then we just use our table up here. So right, we have 2 HCl's for every 1 magnesium hydroxide. And again, we have moles of magnesium hydroxide. We're going to have moles of magnesium hydroxide here and moles of HCl up top, because those are the units that we're looking for. So we have 2 moles of HCl, 1 mole magnesium hydroxide. And then our final step is to take then chlorine, calculate the molecular weight for chlorine, or hydrochloric acid. All right, so this is 35.45. And we have 1.01. There's only 1 of each of those. So we get, again, we want grams now, right? So we have 36.06 or 36.56 grams per mole. The unit we want to cancel is going to go here. The unit we want to end up with goes on top. So we have 36.56 grams HCl for every 1 mole HCl. I'm going to write the answer up here. And we just multiply across the top. So 5.5 times 2 times 36.56 divided by 58.33. You could say divide by 1 divided by 1, but if you divide by 1, you get the same thing. And we get 6 point, how many significant figures do we have? Right, so that's 3, and we have 4. This is exact, and we have 4. So we're going to have 3 significant figures, 9 grams of HCl. Okay. Got to keep moving on unless there are questions. Just another example here. So one component of acid rain is sulfuric acid, which forms SO2, sulfur dioxide, which is a pollutant that reacts with oxygen and rainwater. Which forms when? So we have SO2 reacting with oxygen and rainwater according to the following reaction. Assuming that there's more than enough oxygen and more than enough water, how much sulfuric acid in kilograms, right? This is where I was telling you, can't get a little tricky. How much sulfuric acid in kilograms forms from 2.6 times 10 to the 3 kilograms of SO2. All right, so again, let's highlight. We are given kilograms of SO2, and we are looking for H2SO4 in kilograms, right? So our solution diagram is going to look slightly different. The first thing we're going to want to do, again, you always start with what you're given. Delete these because I'm going to be short on space as it is. We are starting with 2.6, we're starting with, just to do this in units, kilograms SO2. We're just going to take one extra step here, and we're going to convert that to grams of SO2, right? Because our molar masses are in grams per mole. Then we're going to go from grams of SO2 to moles of SO2. From moles of SO2, we want to know, what are we looking for? Sulfuric acid. So moles H2SO4. You made it fit. Now, we've got moles. Again, molar mass is in grams per mole. So we're going to convert first then to grams of H2SO4 from our moles, then to kilograms. All right. We're going to get some class participation on this one.
So to do that first conversion easily, can you just do 2.6 times 10 to the 6th?
Yeah, it will be 2.6 times 10 to the 6th. Right. That will be the resulting answer. So you could just do that in your head, right?
Yeah.
You could just throw that out for sure. But just for the sake of getting everything out on paper, some 6. Oh no. Thank God for undo. Kilograms SO2, right? And so then our conversion factor from kilograms to grams, we're going to have 1,000 grams for every 1 kilogram. Molecular weight of SO2 is going to be 32.06 times or plus 16 times 2. So again, we're in grams per mole. We have grams currently as our units, right? So we've converted from kilograms to grams. Now grams of SO2, so we're going to put grams of SO2 on the bottom. So we're 64.06 grams SO2 for every 1 mole SO2, right? So now we've got units of moles of SO2. And here's the class participation. What is our ratio between moles of sulfuric acid and SO2?
1 to 1 or 2 to 2?
1 to 1.
Yeah, 1 to 1 if you reduce it, or 2 to 2, right? Works out to be the same thing. You can reduce these when you do it. Just make sure you're careful. So we got, I'm going to put 2. again, just for having everything on paper, 2 moles of H2SO4 for 2 moles of SO2, right? Again, this is the unit we have currently. This is the unit we want. Or sorry, this is the unit we're canceling with. This is the unit that we want. All right, so then we can convert and get the mass of sulfuric acid. So 1.01 times 2 plus, was it 32.06 plus 16 times 4 will give us 98.08. Again, we want grams now. 98.08 grams H2SO4, 1 mole H2SO4. And now finally we're going to convert from grams to our kilograms. So 1 kilogram is equal to 1,000 grams. And we can just multiply across the top again. It's 2.6 e to the 3 times 1,000 times 2 times 98.08 times 1, but we ignore the ones. And then we're going to divide by 64.06, divide by 2, and divide by 1,000. So we end up with, again, I ran out of space. Right, remember your sig figs. Started with 2 sig figs. Everything else has more than 2 sig figs. So our resulting answer is going to be 4.0 times 10 to the 3 kilograms of H2SO4 in my sloppiest handwriting possible.
So what answer did you get at unscientific notation? Did you get 3897?
3980.7. Yeah, before rounding. All right, is this making sense? Not too crazy?
Yes.
A lot better than oxidation.
Yeah.
Yeah.
Okay. So suppose we have, yes, okay. So these are called limiting reactants or limiting reagent problems. So suppose we have 3 cups of flour, 10 eggs, and 4 teaspoons of baking powder. How many pancakes can we make? So the trick to these problems is figuring out, and actually, let's actually take a break real quick. Short break, couple minutes. I need to run to the bathroom. So come back at 1:17. Okay. Everybody back? We're ready to go. Keep moving. All right. Let's see here. Okay, right. So, how many pancakes can we make with our 3 cups of flour, 10 eggs, and 4 teaspoons of baking powder? The quick. So basically, you got to figure out which of these is our limiting ingredient. What do we have, right? What are we gonna run out of when we start making pancakes? So you can do something like, well, for how many pancakes that we can make? Let's see, we have enough eggs to make, right, 5 batches. So it's 25, but we only have 3 cups of flour, so we can only make 315. Right, so that's what we're getting to. So you can look at this.
Break down each product.
Yeah, you can look at for each of these how much they're going to make, right? So for 10 eggs, right, it's going to be 2 eggs for every 5 pancakes. I'm just going to abbreviate that from P because we're going to do this a few more times, right? So you can do that one, and you'll get 20 divided by 2. You'll get 50 divided by 2, which is 25 pancakes. Or if we use our flour to pancake ratio, right, we'll get 5 pancakes for every 1 cup of flour. So then we only have 3 cups of flour, so that's 15 pancakes. And for our 4 tablespoons or teaspoons of baking powder, we only have a half teaspoon of baking powder for every 5 pancakes. So if we do 4 times 5, right, so this is baking soda. I'm doing this real sloppy, but it seems like most people get it. So we'll get 20 divided by 0.5, and that's enough baking powder to make 40 pancakes. So what you're doing in these limiting reactant or limiting reagents is you're looking for the one that can make the fewest number of pancakes, or the fewest number of the molecule or your product, right? So in this case, we'd run out of flour before anything else. So the flour would be the limiting reactant, and 15 pancakes would be the theoretical yield. So suppose we cook our pancakes, and we accidentally burn 3 of them, and 1 falls on the floor. Even though we had enough flour for 15 pancakes, we only finished with 11. In a chemical reaction, we would say that the 11 pancakes will be our actual yield, and the amount of product actually produced, or the amount of product actually produced by the chemical reaction. And the 15 pancakes would be our theoretical yield, because in theory we had enough, but in actuality we only get 11. So our percent yield is our percent yield, the percentage of theoretical yield that was actually attained that's a little bit confusing. Our percent yield is the number of pancakes, or the amount of product that we actually made divided by the amount that we could have made. So since we ruined 4 pancakes here, we only get 73% of our theoretical yield. Right? So it's, make sure it's not on the next page, right? So it's actual yield divided by theoretical yield. Actual divided by theoretical. So the actual
Wasn't that
yield.
something on like one of our first labs?
Yeah, the first lab had you calculate. Well, that was percent error. So that's a little bit different. That's where you take. That was like for calculating the density of something, right? So you're given a number. So the actual number is the actual density of whatever metal is 9 grams per mil. What you do is then you say, okay, the actual is 9 grams per mil, and this was the absolute value of 9 minus what you got. So I think it was about 7 grams per mil divided by what you should have gotten. So this is giving you the percent different that you were from actual. So yeah, that was percent error. This equals percent error. This equals percent yield. So the actual yield of a chemical reaction must be determined experimentally. So you can't predict, unless you've done it before, what your yield is going to be for a chemical reaction. And the actual yield is almost always less than 100%. And some of the product just doesn't form. And that has to do with the properties of the reaction. And sometimes you lose product in the process of recovering it. So usually when you do a reaction, you've basically got a mess of molecules and atoms. And so you want to select out then and purify out just the one that you're looking for, just the one that you wanted to make. And you can't always do that. You can never do that 100%. You're always going to lose a little bit. So summarizing then, our limiting reactant is the reactant that is completely consumed, the reactant that makes the least amount of product, right? So that was our flour. And our theoretical yield is the amount of product that can be made in a chemical reaction based on the amount of the limiting reactant. And the actual yield is the amount of product actually produced by a chemical reaction. So then our percent yield is actual divided by theoretical times 100. So what are the limiting reactant and the theoretical yield if you start in this reaction with 1.8 moles of titanium and 3.2 moles of chlorine? So you'll make with your titanium, right? So titanium to titanium chloride is 1:1. Trying to figure out where to write this stuff. Let's just put it up here, right? So this is going to make 1.8 moles titanium chloride. And this is going to make, we're going to make half of this into titanium chloride, right? Because you've got 1 TiCl4 over 2 Cl2. So we're going to actually get 1.6 moles of titanium chloride. So chlorine here then is our limiting reagent. So you can use stoichiometry, right? That's using this. And the ratios from our reaction. And we can find the amount of product that can be made, right? So that is our theoretical yield. And our theoretical yield is going to be equal to the smaller one, right? This is like if we ran out of flour. We're running out of chlorine before we're running out of titanium. I'm pointing with my finger, but you can't see that. We're running out of this chlorine before we run out of titanium. So our theoretical yield is equal to the smaller yield. This is the same question. So just to do it out a little more formally, right? So you have 1.8 moles of titanium, and our ratio is 1:1. So for 1 mole of titanium, we'll make 1 mole of titanium chloride, right? And so we'll make, if we had enough of everything else, 1.8 moles of titanium chloride. But when we look at this for chlorine, we'll see that, just like I did before, 3.2 moles Cl2 for every 2 moles of Cl2, we are only making 1 mole of titanium chloride. So we do 3.2 divided by 2 is 1.6 moles titanium chloride. right? Just like the pancakes. They're just using different names for things. So if we consider this reaction as well, right? We begin with, and you can try and beat me to the answer, of course. Hopefully you are. 4.8 moles of sodium. 4.8 moles Na. We know our ratio is 2 to 2, so that's a 1 to 1, right? But I'm going to write NaF, 2, Na. So we're going to end up with 4.8 moles NaF. Then if we start with fluorine, we have 2.6 moles of F, right? And hopefully you can see what I'm doing here, right? I'm just pulling these numbers off of the table, or off of our reaction here. Sorry, this is F2. All right, so for every 1 mole of F2, we're going to be making 2 moles, right? This is 1, this is 2. 2 moles of NaF. So we're going to get 5.2 moles NaF, right? So then our limiting reactant is going to be sodium. And then our theoretical yield is the amount of our product that we make with our limiting reactant. So this is the limiting reactant. This is our theoretical yield. Whew. All right, we're getting close, and it's only been another 30 minutes, so I think we're doing okay. In many industrial applications, the more costly reactant, or the reactant that is most difficult to remove from the product mixture, is chosen to be the limiting reactant, right? You want to use the least amount possible of the most expensive reagent, or the most expensive component. And if it's hard to remove, you don't want any of that left over after the reaction, or you want to minimize it. And when we work in the laboratory, we measure the amounts of reactants in grams. So we can also find this limiting reactant and our theoretical yields from initial masses, but we have to add 2 steps to our calculations. Those steps being converting from grams to moles, right? Because if we're going to compare anything, we always have to do it in terms of moles. We cannot compare sodium and chlorine based on the number of grams that they have, right? These are fairly close together. But if I pull up this periodic table, I have a slide where it's just all the periodic table, right? So we're looking at sodium. Let me back this up a little bit. Sodium has a molecular weight of 22.9. And chlorine, this is not just chlorine though, this is CO2, right? It's a Brinkelhoff compound. So its diatomic is CO2. We're looking at 35.45 times 2, right? So we're looking at 70.9 grams per mole. So the number of moles that we get out of each of these, even though their masses, the mass of each compound is relatively similar, the resulting number of moles is going to be very different. So let's do this right now. Right, so we're going to start with our grams of sodium. And you could do solution diagrams for these if you wanted to. So you got 53.2 grams of sodium. And our molecular weight for sodium is 22.99 grams of sodium for every 1 mole sodium. All right, so we're going to get 53.2 divided by 22.99. So we're going to get 2.31 moles of sodium. And let's just do this now for 65.8 grams of chlorine, Cl2, right? Because it's Cl2, we need to do its molecular weight, 35.45 times 2, right? 1 for each of those chlorine atoms. We're going to get 70.9. So 1 mole of Cl2 is equal to 70.90 grams of Cl2. So 65.8 divided by 70.9 is going to be 0.9, three significant figures, 928 moles Cl2. Right, so you can see how even though 53 grams actually being less than 65 grams, and they're roughly the same, they're pretty close together, like they're not much more. But when we convert these into moles, now we've got 2.3 moles of sodium, but we only have 0.928 moles of chlorine. And then we can continue this on from here. We can use our ratios, right? So 2 sodiums to 2 sodium chlorides, 2 NaCl, 2 Na, right? So we're going to get 2.31 moles of salt, right? NaCl. And when we do this for chlorine, we are going to get 2 sodium chlorides for every 1 Cl2 atom. So we need to figure out, though, 0.928 times 2 will be 1.856. I'm sorry, 1.86 moles NaCl. So you can see that even though we had more mass of chlorine, its higher molecular weight, its much higher molecular weight, means we actually have fewer actual atoms of chlorine. We just have, each of those atoms is just heavier. So when we do out this math, when we finish out this math, right, we end up with this as our theoretical yield. And chlorine as our limiting reagent. All right, we're at 25 of 36 slides. So here's a reaction where we're synthesizing ammonia, right? I think we used this one earlier. What is the maximum amount of ammonia in grams that can be synthesized from 25.2 grams of nitrogen and 8.42 grams of hydrogen? So again, this is the limiting reagent problem, right? So we're given amounts of both and asked what the maximum we can make is. So grams of nitrogen, and we can do this in parallel too, right? So we can do 8.42 grams of H2 if you want. And I like setting them up like this, right? We can go here, we can go here. All right, so first step, of course, when we compare anything, we have to compare them. We have to compare a molecule to molecule, really. We can't compare the mass. We want to know how many of them there are, right? And that's what a mole is. A mole is telling us how many molecules there are. Okay, so for nitrogen, the molecular weight of nitrogen, and again, sneaky Brinkelhoff, we got 14.01 times 2, right? And so we're canceling grams because we're going to moles. So we can do this as a general, right? So grams, we're going to go to moles here. We're going to go from moles of one of these. We're going to convert each of these into moles of NH3. And then if it asks you, right, you could go to grams. But we're not going to do that. We can stop at moles to figure out how much is going to be made. So 28.02 grams of N2 per mole of N2. Hydrogen will be 2.02 grams of H2 for every mole H2. right? And then we want to convert from our moles of nitrogen or our moles of hydrogen over to moles of ammonia. So let's do nitrogen first, right? So 1 nitrogen makes 2 ammonias. So 1 mole of nitrogen for 2 moles of NH3. And for hydrogen, right, we have 3 now to 2. So for every 3 moles H2, we're going to get 2 moles NH3. We'll see what our answer is here. 25.2 times 2, just doing the top one first, divided by 28.02. 1.3 sig figs, 1.80 moles NH3. 8.42 times 2 divided by 2.02 divided by 3 will give us 2.78 moles NH3. The nice thing about doing it in this fashion, right, where you line up all your conversions first, and then you do all of your multiplication and all of your division at the same time, is you keep it all in your calculator, right? Because you can just you can do 25.2 times 2, 25.2 times 2, hit enter, and then if you have the right kind of calculator, you can just hit divide, and it will automatically take your answer from the previous computation and put it in there. Because when we look at significant figures, for all the math in between, we want to keep track of the number of significant figures, but we want to use all of the digits possible for those calculations to avoid rounding errors. And then at the end, at the very last step, when we have our answer, that's when we round. Sorry, tangent there. So, which of these is our limiting reagent? Ammonia. Or not ammonia, nitrogen. Nitrogen's our limiting reagent. And again, right, so you cannot predict, based on their masses, which one is going to be the limiting reagent, because we have more than, well, about 3 times the amount of nitrogen. But because of these vastly different molecular weights, because of these different mole ratios, we end up not being able to make as much ammonia with even 3 times as much nitrogen. So you always got to go at least up to moles of what your product is. And then sometimes it'll ask you how many grams. Oh, shoot. Yes. So this one, it's asking for ammonia in grams. So we would just take this one step further, right? Nothing too difficult. We've identified now which one is our limiting reagent. It's 1.8 moles of ammonia from our nitrogen. So our theoretical yield will be based off of this 1.8 moles. So 14 plus 1.01 times 3. So this is moles NH3, and this is 17.03 grams NH3 for 1 mole NH3. So do 1.80. So this is probably a good example of where you might encounter rounding error, right? So I rounded this. 1.80 is rounded. So that gives us 0.106 grams NH3. Well, let's see if I had used my unrounded number. Oh, where'd it go? All right, so it was 1.856. If I use this and divide by 17.03, we do get a slightly different answer in 1.
Aren't we supposed to multiply by 17.03?
Yeah, that's what I was thinking too. You've got your.
I mean, you solved my conversion trap, my conversion puzzle.
Yeah, I was scratching my head, but then she beat me to it. So yeah,
Oh, yes. You multiplied by 1701 or 3. Thank you. And I'm glad you caught it because that means you know what's going on. Right. So 1.8. Let's do this. If I had used the whole number, then we would get, right? So 1.856 was the whole number that I got for the previous calculation of this 1.8. No, it's not. What? Did somebody else check that math? Oh, here it is. So it's this times 17.03.
I got 1.798, and then it's multiplied by 1703.
Yeah, 30.6. But I had rounded that to 1.8, right? So if we use the rounded number, is what I wanted to do, 17.03. It actually comes out to 30.7, right? So in this case, it's slight because we only rounded at the very last step. But if you round at every step, those errors are going to add up, and they add up really fast for every computation. If I saw this kind of difference at the end, I probably wouldn't think anything of it. It would be rounding error, right? I'm not being that much of a stickler on rounding. So really either of these, right? So this is the number of grams that we would make from our limiting reagent. Okay, so we have this reaction, the reaction of 185 grams of iron oxide with 95.3 grams of carbon monoxide to produce 87.4 grams of iron. We want to find the limiting reactant, the theoretical yield, and the percent yield, right? So we've been given an actual yield. Sorry, hold on. Highlighted the wrong one. We've been given the actual yield of 87.4 grams of iron. So, and this is a good one. This brings up an important point because as long as you're computing to the same product, it does not matter which product you compute to. When you're trying to determine your limiting reactant, right? Because we're going to do 185 Fe2O3, and we're going to do 95.3 grams of carbon monoxide. This example is asking us about iron, right? So we're going to work towards how much iron there is. But to identify the limiting reagent, you could also calculate these so that you ended with, since we're looking for grams, let's just say we end with grams of CO3. Does that make sense? As long as we do the same thing for both of these, this will tell us what our limiting reagent is, right? Because one of these will produce fewer grams of carbonate. Sorry, that's CO2. One of these will produce fewer grams of CO2 than the other. Similarly, if we instead do, like we are right now, to calculate the number of grams of iron, one of these will give us, and it'll be the same one, one of these will also produce fewer grams of iron. So we don't need to, say, calculate how many grams of iron and CO2 can be made with this amount of iron oxide and then also this amount of carbon monoxide. You only have to compare to one. It just has to be the same. Okay, so again, right, our steps are we've got grams. We're going to go to moles. We want to convert both of these to moles of iron. And then eventually we'll take, because we don't need to go all the way, we can just go to moles of iron. We'll take the limiting reagent and we'll finish that one out to calculate grams of iron. All right, so we're going from grams to moles. Periodic table time. Iron is 55.85. So 55.85 times 2 plus 16.0 times 3. This is going to be, again, right, we're going from grams to moles, so we're going to put this on the bottom, 59.7 grams Fe2O3. 1 mole Fe2O3. For here, we've got, well, 12.01 plus 16, so we're going to get 28.01 grams of carbon monoxide for 1 mole carbon monoxide. And then, right, so we've gone from grams of our reactants for each of these, and we want to go to iron. We want to go to moles of iron, right? So we got moles of our reactant, go to moles of iron. For iron oxide, we're doing 1 mole Fe2O3 to 2 moles Fe. And we're going from carbon monoxide will be 3 moles carbon monoxide to 1 mole iron. And it's at this point, right, where we're going to stop and we're going to see which of these is our limiting reagent. So 185 times 2 divided by 159.7. Right, that'll give us 2.3 2. We're going to do 95.3. Nothing on top, so just divide by 28.01. Divide by 3. We're going to get 1.134. Well, 1.13. So then our limiting reagent then is our carbon monoxide, right? Because we've got fewer moles of iron coming from our carbon monoxide. Now,
and then to find the theoretical yield and the percent yield, you're going to have to continue that out onto the your final step. Okay.
Yeah, so that's just to get us to there. And now we go one more step with this one to get our theoretical yield. Iron again with what, 55.85? I'm going to do it right this time.
Yep.
And then 1 mole iron.
So on my the periodic table that I'm using says 55.93. I'm not using it out of the book, so am I going to get that wrong, I guess, or? Yeah, see, yours says 8.5, but mine says 3. I don't know.
How about this? I will post this periodic table from the book, so you can.
I want to print it out.
If you got a different one, then you could print it out, or you could have it on your phone, or even,
Cool.
Let me make a note, because that is something that I will very easily forget. Sheesh. All these feel so popular, getting all these text messages. Rare occurrence. Okay. Upload textbook table. All right. I will upload that periodic table, and so you can have the right one because of your ridiculous version of that PDF you got. Okay, so 63. We're going to get 63 63.1 grams as our theoretical yield, right? Darn tootin', there ain't no space. Well, okay, so our theoretical yield, or our percent yield, right, is our theoretical 63.1 divided by our actual 87.4. So our our percent yield then, right, and then you multiply by 100, will be 72%. And I guess if you want to be real specific about sig figs, and I hope you do, 72.2%. Excellent. Oh man, we're going to do enthalpy right now? All right. Chemical reactions can be exothermic, they emit thermal energy, or endothermic, they absorb thermal energy. The amount of thermal energy emitted or absorbed by a chemical reaction can be quantified with a function called enthalpy. So the enthalpy of reaction, that's this delta H Rxn, is the amount of thermal energy or heat that flows when a reaction occurs at constant pressure. That's kind of a lot. Just remember, that's the amount of energy that flows. So the sign of delta H, positive or negative, depends on the direction in which the energy flows. Depends on the direction in which the energy flows. Energy flowing out of the chemical system is like a withdrawal, and it's a negative sign, right? So if we've got our system and heat is leaving the system, we are subtracting heat from the system. We got our system and our heat is going out, right? So now we would say that the energy within our system, energy minus delta H, that's the heat leaving, equals our total energy. Or maybe our energy, call it our energy final, right? So it's our energy, our initial energy, we're losing heat, then we get our final energy. If energy is flowing into the system, it's like making a deposit. We're adding to the system and it carries a positive charge or positive sign. So this is negative delta H. If we have our system and we're adding heat to it, then our EI plus delta H equals our energy final. So in an exothermic reaction, energy is released into the surroundings. So we're sending energy out from our system. We're releasing energy that is then a negative delta H. In an endothermic reaction, energy is being absorbed, right? We're adding energy. So you can think of this as like our energy, right? This is our energy level. We're going from this energy level down to this energy level. And that heat then gets released to the system. If we're going then from our reactants and then increasing to the level of the products, that's heat being added to the system. So this is exothermic, right, on the left, and then we have endothermic on the right. So delta H is, right, negative for exothermic reactions. The enthalpy of reaction for the combustion of CH4, which is the main component of natural gas, which you got in your stove. Well, if you're lucky enough to have an electric stove. I wish I had one. The delta heat of that reaction, right, is negative. Right, we have a negative sign, so we're releasing that energy into the environment from the stove, from that reaction. And the magnitude, right, so this 802.3 kilojoules of heat, that's the amount of heat that's released when we react 1 mole of CH4 with 2 moles of O2. So this amount of energy here is tied to the amount of products, or the amount of reactants that react. So if we were to have 2 moles of CH4 react completely with 4 moles of O2, this would be negative 802.3 kilojoules times 2, right? Because I just multiplied these by 2. That'll increase our energy released by 2. So then if we've got a positive delta H of the reaction, that reaction is endothermic. So the enthalpy of the reaction between nitrogen and oxygen gas to form nitrogen monoxide is endothermic, right? Negative charge, or negative sign here. I keep saying charge. So the magnitude of delta H tells us that 182 kilojoules of heat are absorbed from the surroundings when we have 1 mole of N2 and 1 mole of O2. And again, if we double those, if we have 2 mole N2 and 2 mole O2, then we have plus 182.6 times 2. Or if you have a half, right? So if we did 1.5, then we're going to multiply that delta H by 1.5. The amount of energy heated or absorbed when a chemical reaction occurs depends on the amounts of the reactants that actually react. So again, you can think of this, you can really kind of think of these reactions as N2 plus O2 reacts to form, you're going to form 2 moles of NO, right, nitrogen monoxide, and you're going to form 182.6 kilojoules, and delta is also used for heat, right? Kilojoules of heat. So if we do a limiting reactant problem and it asks us what is the maximum amount of heat released from this amount of nitrogen and this amount, or sorry, heat absorbed for this reaction, right? So we're absorbing heat, we're absorbing energy. What's the maximum amount of energy that could be absorbed? This is going to be a limiting reagent problem. Yes, the magnitude of delta H is for the stoichiometric amounts of reactants and products for the reaction as written, and tells how much energy is transferred for the molar amounts in the balanced equation. So let's look at this equation, right? So we have this balanced equation, and we have a delta H. When 1 mole of C3H8 reacts with 5 moles of oxygen to form 3 moles of CO2 and 4 moles of H2O, we release 2,044, right? We're releasing because it's negative. If this is negative, this is exothermic. So we can use these ratios to construct conversion factors between amounts of reactants or products and the quantity of heat exchanged. All right, so let's calculate them. The heat associated with a complete reaction of 155 grams of ammonia. Okay, so we've got 155 grams, NH3. And we know, right, that when we do any comparison or when we do these calculations, right, so basically we're going to compare the number of moles of ammonia to the amount of heat released. So again, we're always going to moles. We're just always going through mole town. So times 1.01, plus 1.01 times 3. All right, so I'm converting this into moles. I'm also deleting everything on accident. So 17.04 grams NH3 is 1 mole NH3. Now, for how many For every 4 moles, bump the microphone, for every 4 moles of ammonia, NH3 that reacts, we're going to get 906 kilojoules released. Again, it's negative 906. So that means that we are releasing energy. It's endothermic. It's leaving the system. It's being subtracted from the system. So we use this ratio, right? We use 4 to 906. So 4 moles NH3 is equivalent to not equivalent to, but releases 906 kilojoules. So now we can just finish out our math 5 times, and don't forget the negative sign, divided by 17.04 divided by 4. So we're going to get negative 2060. So 2.06 times 10 to the 3 kilojoules released. And so you don't have to do that just with ammonia here, right? You could say you've got 155 grams of oxygen. How much heat is produced when you react that much oxygen? Or you could say 155 grams of nitrogen monoxide, right? How much, or 155 grams of nitrogen monoxide is produced, how much heat is released, right? So you can do that for any single one of these. And as long as you have a starting quantity, you can get to really any piece of the chemical reaction using stoichiometry, right? So with this amount, we could calculate the moles of oxygen required for this reaction. We could calculate the grams of oxygen required for this reaction. We could calculate the number of moles of nitrogen monoxide produced or the number of moles of water produced, right? And from there, grams. So stoichiometry is a really, really powerful tool if you understand how to manipulate it. I think we got one more practice problem here and then a final slide. And then this very long day will be done. Well, you'll go off and do homework and other assignments, and I will grade assignments and write the exam for tomorrow. But the mass of butane in grams is necessary, or what mass of butane in grams is necessary to produce 1.5 times 10 to the 3 kilojoules of heat? And what mass of CO2 is produced? All right. So, how the plot thickens, right? So we're given heat now. We've seen how to go one way with heat, right? We've gone from an amount of one of the reactants to the amount of heat. But like I just told you, if we have any piece of this reaction, we can calculate all the other pieces. So we're going to start with what we have, though, right? So we have 1.5 times 10 to the 3 kilojoules of heat, right? Let's get one of these guys in here. So let's see, what is our next move here, right? 1.5 kilojoules is not the same as this, but we are producing heat, so that's important, right? We're producing heat. So, like I said before too, you can kind of think of this delta H as part of the reaction, right? So this is just another coefficient for the element, just metaphorically speaking, the element of heat. That's part of this reaction. So we want to go from heat, we want to do butane, but we also want to get the mass of carbon dioxide. So let's do butane first. So 2,658 kilojoules is what the heat produced from 4 moles of butane. So this is butane. So we have kilojoules, right? And we want moles of butane. So we'll do negative 2,658 kilojoules, 4 moles butane, C4H10. And then from there, now that we've got the moles of butane, we need 12.01 times 4 plus 1.01 times 10, right? Because we want the grams of butane. Sorry, we want the mass, right? Mass is in grams. So we're doing 58.14 grams C4H10 is 1 mole C4H10. Now we can just do 1.5 e to the 3 times 4 times 58.14 divided by, well, I guess here's where the negative kind of gets a little bit weird, and so you have to know what you're working with, right? Because if we throw the negative in there, that gives us a negative mass of butane, but that doesn't make sense.
It says produce, so it should have started with negative 1.5, right?
I think that is the key, right? So it's either that way or you're thinking about it backwards and you're putting the heat back in, so you're making it positive, but right. So we've produced this. We've removed negative 1.5. Thank you. But this is too where, like, when you look at your answer, if you get negative 131 grams, and we actually only have two significant figures, so 1.3 times 10 to the 2 grams, you can't have a negative mass. So now we've calculated the number of grams of butane. And then it's basically this exact same process, right? So we can, with the magic of technology, actually, let me shrink this first. Copy, paste, right? Very much the same setup, but now instead of, we're going to erase this, right? Because we're not doing that. And we're going to erase this because we're going to carbon dioxide instead. So I guess two ways you could have done this, right? You could have taken this mass now of butane and then gone from butane to CO2. Or you can just start over again with your energy, and this is actually still going to be 4, right? 4 moles CO2. You start over with your energy and just calculate it. And we're going to get 12.01 plus 16 times 2. So 44.01 grams CO2, moles CO2. All right, so negative 1.5 times 4 times 44.01 equals that, divided by negative 2658 to get, again, 2 sig figs, 9.9 times 10 to the negative 2 grams CO2. Yep. There you have it. That's stoichiometry. If you can understand that basic principle, well done. If you can't get it yet, if it's still a little bit over your head, or if you get to the homework problems and you struggle with it, there's a reason that this is like the cursed word of chemistry. People talk about, stoichiometry. Hate stoichiometry. It's being dramatic. But it is difficult.
I'd rather do this than that last thing we did. Long.
The oxidation reduction? Yeah. I think stoichiometry ends up being people's least favorite because you do it so much. Do it a lot. So often in the homework, I guess this is just a note to say that the absolute value of heat is requested, and words are used to convey the sign of the heat absorbed or given off in the reaction, right? So you could say emitted, right, would also be like given off. These are all things that are going to like convey this, that you're going to have a negative delta H. or you could have absorb. There will be other words too. Or you'll get something like, after the reaction, the room was like cooled, or like anything, right? You got to be looking on the lookout for these too, right? Because this would be positive delta H. So exo, endo. Just got to be aware of those kinds of keywords and be looking for those. Okay. Right? And then it's a blank page at the end. Man, are there any questions? Thanks for sticking around for 4 hours. Oh,
Yeah, that was a lot today.
so much. It's just maybe I should have like tacked on the first half of that redox stuff yesterday after the lecture, because we got done. I think we got done at noon yesterday. It's only 2 hours, so I saw 30 slides and I thought, this will go quick, and I forgot how long redox reactions go.
4 hours is pretty normal for a 4-week class. My
Okay.
bio was every day from 8 a.m. to 2 p.m.
Wow.
So 4 hours is pretty good.
All right. So we're doing all right then. Yeah, so just a test tomorrow. And yep, should be around 50 questions. You'll get at least 2 minutes per regular question. Maybe longer if I give one of those redox reactions. And I will get this uploaded as soon as possible. Huh?
Please do not do that to us.
The redox reactions aren't bad, they're just tedious. So yeah, it would take quite a bit more time to make sure we had the ability to
Right.
do it all and check all of the, it's not really math, but just placement of all the letters and everything.
Yeah. Tedious is exactly right. Tedious and a lot of minutia, a lot of very, very fine details that you got to pay attention to.
Apparently my dog doesn't like them either. That was her protest.
All right. Well, yeah, I guess I can't do it then. No, yeah, again, probably, individual steps or pieces of it is, I think, the better thing to test on, really. Okay. That is it for today. I will, oh, actually, I need to make an announcement about this. Monday's lecture will just be recorded. So I will actually record that tomorrow and post it. I'm going to be out of town on Monday. I will be able to respond to questions, though. Still ask me questions. I will be available for that. But I won't be able to live lecture. So I will hear from you devoted few, on Tuesday.